All right, so welcome everybody to the first workshop on learning 3D representations for shape and appearance, or 3DReps for short. My name is Srinath Sridhar. I'm a postdoctoral researcher at Stanford University. Joining me today is my co-host, Or Litany, who is a research scientist at NVIDIA. So what is the 3DReps workshop all about? Now, as we all know, in the recent past, there has been a resurgence of 3D computer vision problems in our community. So here's just an example from the last two CVPR conferences showing a list of the top 5 keywords. And as you can see clearly, 3D is among the top 3 of the keywords that occur in submissions and accepted papers at these workshops. So clearly there is a lot of interest in our community in working on 3D problems. And this, together with interest in deep learning techniques, has resulted in a wide range of papers on a wide variety of 3D representation problems. For example, for representing 3D shape or for representing appearance. So the goal with our workshop was to bring together different people, different researchers working on diverse range of problems related to 3D computer vision to the same venue. So our goal really is to bring together a diverse variety of researchers working on a diverse variety of sub-problems to the same room. I'd like to take this opportunity to thank my co-organizers, Leo Gibas, Or Litany, Tanner Schmidt, Vincent Sitzman, Shubham Tulsiani, and Gordon Wetstein for putting together a really great technical program. And the way we are achieving this goal of bringing together people from different communities and sub-problems working on 3D problems is by having a technical program with 3 components. Now, before I give you an overview of what these 3 components are, I just wanted to point out that the full workshop program is available on our website, the link to which you see on the top of the screen share. Please visit this website to get the most up-to-date information, and you can also choose your time zone so that you don't lose track of your favorite talk or poster. The workshop will be organized into 2 sessions. The first session is the session that you are in right now, which will last for 3 hours. And the second session will happen in 16 hours from now. And again, please visit the website to get the most up-to-date information about the timing of the workshop in your local time zone. So what are the 3 components of our technical program that aims to achieve our goal of bringing together researchers working on diverse variety of 3D problems? The first is a series of invited talks by 7 invited speakers. 3 of our speakers will be speaking today in the first session, and the remaining 4 of our speakers will be speaking in session 2, which will happen in 16 hours. So this is the first part of our technical program. The second event in our technical program is a panel discussion with a subset of our invited speakers. This panel will be hosted by Gordon Wetstein, my co-organizer, and this will happen in session 2. So this will be the last hour of the workshop. And the final technical event of the workshop is a set of 14 invited posters. These are papers that have previously been published in the area of 3D representations at many conferences in the last couple of years. And this will happen in session 1. So that is today. This will happen in the next, this will start in about 1 hour. I must point out that these 14 papers, we chose these 14 papers as being representative of the kind of problems that people work on 3D representation. And of course, there are a wide variety of other papers that this poster session does not cover. We invite your feedback on what kind of papers we can include in the next iteration of our workshop, the second 3DReps workshop. I'm going to hand it over to my co-host, Or, to tell you a little bit more about the logistics of the workshop and how you can participate in the interactive poster session. Over to you, Or.
Thank you, Srinath, and welcome everyone. Yeah, exactly as Srinath said, we've tried our best to organize a very special workshop for you today. We'll utilize 2 virtual platforms, so it's important that everyone plays nice and we keep a certain behaviors or agreements between ourselves. So the first one is this Zoom channel. And by now, everyone should be fairly familiar with the webinar, but you have this Q&A button at the bottom. Use that Q&A button to ask questions. We will not unmute you, but instead we will track the questions asked during talks, and we will help the speakers by reading them the questions and having them answer the questions that will fit in the 5-minute amount of time after every talk ends. We also utilized a fairly new platform that probably most of you are not familiar with. It's called Gather. I'll explain what that is in the next slide. Just bear with me for a second. Just one note before I explain about that. Any discussions that you are engaged in with fellow researchers, maybe keep some local copy of your discussions, because we haven't made sure to keep those around. We just you're responsible for your own discussions. And another request is please use your full name. It makes it easier to communicate with others, and also to return to those lost chats that you can re-find again. So Srinat, can you please change the slide? Thank you. So this slide, in this slide, I'll try to explain quickly what is Gather. So in this slide, there's a link here to the platform, to the Gather platform. And basically, you don't need any account. Once you click the link, you just enter a virtual world that looks like a computer game from the 1980s. Please use your full name. It will make it easier for others to find you. But now, again, there's no need to open any account or set up any password. On the left, you'll see the screen. You'll see once you enter the virtual platform. So what's going on there is that right in the middle, you'll have this little avatar. You can modify the character that you have, and your name will appear above that avatar. You use your keyboard arrows. So it's important that you use a PC for that. Use your keyboard arrows to navigate the room, and use the X button in your keyboard to interact with assets. For example, here, you can see that green lighted TV screen. If you press X here, that will take you directly to the YouTube live stream of this workshop. Now, if you move your character all the way down to the bottom of your screen, you see that little posters sign with the arrow pointing downwards. That will take you to that screen on the right. The screen on the right is essentially a virtual poster, like a hall with posters, a poster room. Somewhat resembles the poster rooms we're used to in real conferences. There's an interaction distance. So if a fellow researcher passes by you, your videos will be available to each other. So you'll be able to interact, see each other, and talk to each other. You can control that interaction distance by using that button on the bottom of your screen. Have this radar-looking type of button. If you press that, every click will change the interaction distance to get it smaller or larger. So that's one thing important to know. Every poster presenter has this designated place for him to stand next to a small podium thing, and everyone that stands on the same color will be able to interact with each other. So you'll be engaged in a conversation. This is like sharing a Zoom room together, only you don't have to click any additional link. You just press X on your keyboard, and then you can interact. If you just stand on the color dot, and then you can interact with each other. If you press X, that will play the video of that poster. Okay, so you have that option as well. You don't have to go to the presenter and ask him for a walkthrough of his presentation. You can just click X, and you'll see the video. So that's basically all you have to know. Srinat, can you please click one more? Okay, so with that, I'm happy to pass the mic to Professor Leonidas Gibas from Stanford University to give some opening remarks on this very interesting and fast-moving field of 3D representations. To you, Leo.
Okay, can you hear me okay? Okay, thank you all, and Srinat for doing the bulk of the work in setting this nice workshop up. So on my side as well, I'd like to welcome you to the 3DReps workshop, and like all of us, I'm looking forward to the great talks we have lined up in the two sessions and the posters as well. I thought I would take just a few minutes to make a couple of comments about this area, my comments will be partly historical and partly philosophical. And I want to start by saying, of course, the area of representations of shape and appearance is central to computer vision. And in fact, I think we are almost exactly at the 50th anniversary of the seminal paper published by Tom Binford, also from Stanford, on generalized cylinders that had a very large impact in the field back then. Now, actually, 50 years ago, it's not going back enough. In fact, 20 years before that, in the early 50s, people like Pierre Bézier and Pierre de Castelnau in France started thinking about how to represent shapes in a computer so they can be manipulated for design purposes. And their work gave rise to splines and the whole area that is still going strong called computer-aided design. So one interesting aspect here is this. In computer vision, the data representations we use have been largely gated by the sensors we have. I mean, we have cameras, both still and video, so typically what we represent is arrays of pixels or temporal sequences of such. But back in those days, there weren't 3D sensors, so 3D representations were designed to be more abstract because they had to be invented from scratch. And in fact, there were not just one, but many that came up. Even from the very early days of the CAD field, there were two branches. There were the surface modelers, the boundary reps, people who liked like the triangle meshes we use today, that represent the shape as the boundary of a surface in 3 dimensions. And the other camp was the volumetric people, the solid modelers that like to represent shapes as volumes. And it's actually quite interesting that those communities persisted over many, many decades. They're still alive and going strong today. And in fact, each developed their own journals and their own conferences, and some with different set of tools, even though ultimately they talk about the same 3D and the same shapes. And the reason for that is that each of those representations has some advantages the other did not. Boundary reps made it much easier to edit the geometry locally, while solid representations were much better for global operations like unions and intersections and other Booleans. In fact, even within the boundary branch of the tree, there were multiple representations underneath. You all know about parametric models, where we represent a surface by mapping a parametric plane by some functions into 3D space. And on the other hand, we have the implicits, where we represent a surface as the zero set of some function defined over 3D. And again, each of these has advantages and disadvantages that I will not really try to go into right now. So those communities persisted, and actually there was a lively industry of interconversions between them and so on. And then as time elapsed, we started to get 3D sensors. So now we got kind of representations that are closer to the sensors, like voxel grids and point clouds. But even on the mathematical side, the continuous side, people continue to innovate, to invent things like subdivision surfaces and multi-resolution approaches to geometry that have many advantages. And that's what the world was like maybe up until the late 80s or so, until kind of machine learning came along, and then the space of representations exploded, because now we had essentially a separate representation for every problem. For every task we wanted to solve, and for every data set, we built a customized representation for that. And now we didn't have 5 or 10, we had millions of representations. You may wonder whether that's a good thing or a bad thing. I think there's both positive and negative aspects to that. But clearly, there was a need to bring some coherence into this space. And one way to do that is to try to convert from these latent representations to more traditional ones. In a particular conversion that has been very, very successful in the last few years is conversions from latent to implicit. There have been very successful approaches that do shape generation by learning deep nets that can convert latent vectors into implicit functions. And the great advantage here is that even though the input can be a discrete representation, like a point cloud or a voxel grid or just a small number of points, when it's converted into this representation, it becomes now a continuous function that can be rendered at various variable scales and resolutions. I think a very exciting direction going forward is the possible intermixing of latent and explicit. I think a very good example of that is the deep voxels work from Gordon Wexton's group here at Stanford. Essentially here you have a representation that is built on top of a tiling of real space, but in each cell of that space, you now have a latent vector that encodes both geometry and appearance. And having this mixed representation is really helpful when you want to compute different views of the scene, because now essentially the renderer, the neural renderer can take advantage of the geometric relationships between the voxels to compute, occlusions and so on. So I think really this is a very, very exciting time, a very, very exciting area with many, many opportunities. And let me end with three comments. We are not the only community to be encoding things. For example, our friends in cryptography also like to encode things for different reasons. But one area they have developed is something called homomorphic encryption, where they want to be able to encode things and still manipulate them. And I think this idea is also important for us. Can we find latent representations where it's possible to do some manipulation at the encoded representation level? People have aimed for that through, I guess, what's called factoring the representation, where maybe perhaps every dimension of the representation represents a different attribute of the object, and these are all knobs that can be manipulated independently. I think although this is an interesting idea, it's probably not fully realizable in practice, because attributes are not fully independent. Some depend on others. And this raises the question of how can we represent a mixed setting where we have perhaps some independent dimensions and some other dimensions that are not at the same standing, but depend on the previous independent dimensions. That's a challenge, because the way we typically do latent spaces today is as a Euclidean space of some dimension where all dimensions count equally. And perhaps we have to think of different mathematical objects that can act as latent representations. Having all these representations may seem overwhelming at times, but it can also be an opportunity, because even for a given task, we can perhaps combine representations for useful effects. Perhaps one can view representations as different views of an object. And therefore, together, they give us more information than one view separately. And finally, there's other areas in mathematics where the notion of representation comes up. One of the famous ones is group theory, and there's an area called group representations. The idea there is that a group is mapped to a bunch of matrices that multiply by the same rules as the group elements. That's a representation. And again, this brings attention to having a representation that structurally has similarity to what's going on with the real data. An interesting aspect in group representations is that, well, there's many of them, but they're all can be decomposed into so-called irreducible representations. There's a set of base representations so that every other representation can be composed in some clean way from the base representations. So it's interesting to think about whether perhaps in machine learning also we can have essentially a basis for the representation space, so that any representation that is useful for a particular task can be composed out of some base representations. Anyway, I'm just mentioning those things to indicate how rich this area is, and I think how much opportunity there is to do novel and interesting things. And with that, I'll pass the talk back to Or to Srinath.
Thank you so much, Leo. This was fascinating. Thanks for the introduction. And with that, I think we're ready to move on to our first speaker, Professor Kristen Grauman. I'm very excited to have you here. So Kristen, maybe while I introduce you, you could set up your, unmute yourself and set up your presentation. So Kristen will talk about sound and space, 3D audiovisual learning. Kristen is a professor at UT Austin and also a research scientist in Facebook AI research. She received her PhD at MIT. She's an IEEE fellow, AAAI fellow, Sloan fellow, and recipient of the PAMI Young Researcher Award and IGCAI Computers and Thought Award. She and her collaborators have been recognized with several Best Paper Awards, including a 2011 MAR Prize and a 2017 Helmholtz Prize, Test of Time Award. Kristen, the stage is yours. Because we're a few minutes behind, don't worry, I will add that time to your presentation. And also, I will give you a 5-minute notice before your time's up, so you know to wrap up on time. The stage is yours.
Okay, great. Thank you, Or and Leo and the rest of the organizers for having me here. I think you can see my first slide. Everything okay there?
Yes, we can see and hear everything.
Good. And there will be sound, so if I start playing sound and you can't hear, please jump back on and let me know. I think, actually, let's double check that. Yeah, well, we'll check. I'll double check that when we get to some sound. Okay, so the theme of this talk is about understanding 3D in new ways based on what we hear. So sound in space, 3D audiovisual learning. And to start off, let's think about what sound is going to do for us. Trying to advance my slides, 1 second. There we go. So what are the spatial effects in audio? So if we think about the 3D environment, we're going to receive information about different factors. The geometry of the space around us will affect what we hear. So will the materials of the big surfaces in the space. And then, of course, our position within that space with respect to the sound sources. And then at the same time, then we have our sensing that gives us direct spatial cues because of the way we receive sound in a multi-channel way. So in this picture, looking top down at a human head, we know that the difference in time or the difference in intensity with which our two ears receive sounds will give us important signals about where that source is in the world with respect to our head. So these are the different factors that are all going to be in play, and we want to capitalize on these not by themselves, but in conjunction with what we can see. And so that's really the theme of the talk today, is thinking about sound in 3D spaces. And qualitatively, the things we can expect to learn when we model the audio and visual together, respecting those factors, well, one is to learn about where things are in the world. So if there's a phone ringing somewhere, we should be able to sense it both by hearing it and seeing the space around it, us, and eventually that object. There's also elements you could expect of safety. If I know what sounds and sights I'm seeing here or there, this may affect my agent's behavior to be safe. There's semantics in sound. So not only the spatial information, but the spatial information linked to what are these objects that I'm hearing from different parts of a 3D space. And finally, geometry and materials themselves we could sense. So in this talk, I'm going to be covering a few of these through some very recent work that we've been doing. And the first one I'm going to talk about deals with the geometry and materials element. And this is work that we are presenting at the main conference this week called Visual Echoes. And it's done by Rohan Gao, Carl Schisler, Shannon Chen, Ziad, and myself. All right, so in Visual Echoes, we are thinking of an agent in a 3D environment where it can learn about the space by both sight and sound. Now, in this case, rather than passively hearing what's in the environment, we're going to think about an agent that emits sound into the environment in order to hear the echoes that come back. So this is an agent that can emit some kind of sound. Here I'm showing a frequency sweep across different frequencies, so then we get a rich echo back. And it's well known that echoes could give us information about space, and in fact, it's already known by Hollywood. So if you remember this older movie called Daredevil, there's a character who can see by listening. So he's lost his ability to see with his eyes, but by actively interacting with the environment acoustically, this character receives some 3D sensing about the world. So let me play a very short clip, and here you can tell me if you can hear or not. Okay, so first a question, could you hear the sound?
We could hear the sound at the very end. I don't know if this is because some delay between the audio and video, or was that intentional?
Okay. No, there was sound in most of it, but I think it's fine. It's probably the best we'll get, so that's fine.
Okay.
If you're getting some sound, I think this is the best we'll get on Zoom. Okay, so we could see the space, by hearing it, the reaction to the vibrations when he hit his stick on the gate there. And we know that animals and even people can do this through echolocation, so emitting sounds and then receiving these reflections. So echoes reveal environment shape, and this is exactly what we want to be able to capitalize on. And so here's our idea, is to perform feature learning in a self-supervised way through echolocation, and then to explore how such an encoding that we learn with sound can benefit downstream tasks that are spatial in nature when there's no sound as part of the observation. And that includes depth prediction, surface normal estimation, and even navigation. So the key insight for this visual echoes work is to think about feature learning through acoustically interacting with the physical world. Okay, so how to get there? So one of the precursors to try and explore this was to have sound measurements in conjunction with the visual measurements. And then some of our other recent work that we're presenting at ECCV, we've developed a sound spaces audio simulator. So this is audio renderings for a set of visually realistic 3D environments, namely Matterport and Replica. And now we're outfitting them with pre-computed audio renderings that are acoustically realistic, meaning they respect the geometry of the space, the materials, where the source might be. And they produce for you a binaural sound measurement, binaural meaning a waveform for each ear, in real time for any sound that you wish to render. So this is done by pre-computing room impulse responses, which means now you have a function sitting at any of the positions that are shown in my photo here, from which you could render the sound for a waveform you've chosen by convolving with this room impulse response function. And finally, this is a setup that's now compatible with Habitat, so we can integrate this with, for example, DeepRL agents that are trained in Habitat. So in this picture, just think of this sensing now that sound spaces gives you is to receive the proper sound. If you are to place your camera at any one of these black dots, if the sound source, for example, were at the center of this red spot in the heat map, now your sound received would be reflected here, as seen now just in terms of intensity change, if you were to be at any of these points. Okay, so you're receiving 3D spatial sound in a proper way with respect to geometry, materials, and your own camera position. Now with this sound spaces, in this first step I want to show, we're doing echolocation. And so I'll play this short clip, and within the limits of what Zoom will relay to you, you're going to hear some somewhat quiet chirps, which is the agent or our system emitting sound into the environment, and then it's going to be coding in with the depth map that's also received, just to give you a sense of what it means to move throughout this Matterport environment and get these sounds back in terms of the echoes. So here, let me play it now. Okay, so in there, I hope that you could hear some little chirps repeating, and then you're seeing the depth responses in that environment. So what's really happening then in our method during training is that we'll take an agent through any such environment in this set, and at every position that it stands, we'll capture the RGB view as well as the depth in that direction, and as well as the echoes received in the left and right ear. So for example, looking top down at this environment on the left, if the agent was standing at that crosshair, then looking in one direction, it'll see this set of views and receive a certain set of echoes. And then if we would rotate that agent here in 4 cardinal directions, we can do the same. So collect what the view looks like, what the depth looks like, and how it sounds from an echo. Right, so this is just getting the data for the linking between what we see and what we hear from echoes. So finally, the main idea then for visual echoes is to construct a self-supervised visual representation using this data. And our key idea is to set up a self-supervised task, which is to know the congruence or incongruence between the echo we hear and the view we see. Okay, so during training, the agent system will see some egocentric RGB view, and we're going to be training a visual encoder on it. We'll call visual echo net. It'll also hear these echoes. And so from the echoes, we're extracting these spectrograms for the left and right ear. And now here comes the task. During training, we want the system to be capable of saying whether or not those two streams are congruent. So it may be the case that the echoes received go in the same orientation as the agent's current view, or it may be that these are echoes that we've sampled from the agent's perspective if it were to turn by 90 degrees or to face the other direction or to face 90 degrees to the left. And the self-supervised classification task is to take both of these modalities and predict which of those directions is correct. In other words, is it aligned or is it off by which of those different degrees? So this is what it's going to be asked to do during training. Now what it means for the visual encoding is that if it's going to be able to predict the alignment between these two correctly, it needs to be able to pull out of the RGB those things that allow it to capture this congruence with the sound. So in other words, if it can interpret the spatial layout of the scene from visual information well, then it will be able to do this task. And if it can capture that information well, that means we're left with the visual encoding that's been enriched by this audio during training alone. So in fact, the product of this approach is not a multimodal system, but instead a visual encoding that will take RGB images alone to do a more spatially enhanced encoding of that input. Okay, so visual echoes now is a RGB encoding that we've learned when during training we experience this acoustic interaction with the environment. But now during testing, here's where we do some downstream taps that require good spatial understanding. So the first one we looked at was depth estimation from monocular input. And here notice that we're asking to have learned these representations from simulated environments, these scans from Matterport with our audio renderings. And now we're testing on real-world photos from NYU in this case, from the NYU dataset. And the depth maps produced by our approach are down at the bottom. For contrast, the row just above that is looking at what happens if rather than pre-train with this visual echoes net, we were to just try and learn this task from scratch. And what's really exciting is that we can get better depth estimates for this task if we have this pre-training with self-supervision from visual echoes. Okay, so we're dropping the echoes, there's no sound at test time, we're going to real photos, but now we've helped this representation along because we understood the echoes during training. Now I mentioned depth prediction, it does get better and it's not only better than Scratch, sometimes even competing very well with heavily supervised pre-training approaches. But we've also done this task with surface normal estimation, finding similar things, as well as visual navigation. And the key thing of these results is getting competitive, even sometimes better than supervised pre-training. Okay, so this was visual echoes, looking at how to acoustically interact with the scene to gain a better visual encoding that respects things about the 3D environment and its materials. And the next example I'm going to very briefly touch on will move towards semantics and localization of objects, and this time in video. So here this is work that we presented recently called 2.5D visual sound. The idea is that, as I said in the beginning, we humans are receiving spatial sound because we have two ears, and we get a waveform for each that will then allow us to spatially sense the environment. Now, many videos would be accompanied only by single channel audio or monaural audio, which is not spatial. It will collapse all that information into a single channel. So our goal is to enhance monaural audio to make it sound like binaural sound. So we want to lift it from this single channel input to a multi-channel output. Now that can sound crazy at the surface, but of course what we have to unlock this is the visual stream. So in the example I had just shown you, visual echoes, we were able to use audio to improve a visual encoding. This one's kind of the reverse. We're using the vision to unlock the signal in the audio input. Okay, because the vision actually allows us to see where objects are. So if hearing a flat audio without spatial, but also seeing what's happening in the scene around, The idea is we'll be able to learn what the spatial sound would be. Okay, so that's exactly what we did. Using binaural audio captured with the rig like you see there, we can start training a model by taking just the mono audio as input, taking the visual frame alongside it, and then training a network that does this lifting or conversion from monaural to binaural. So during training, we know the right answer. We've captured that binaural sound for that video. And so we'll train this network in order to produce that correct output, such that now at test time, if we have just a video with monaural audio, we can return that immersive spatial sound. Okay, so this we've done some video examples. Really, the only way you're going to hear these right is with headphones and from the video file itself. We will only hear a little bit of intensity changes with through Zoom. So if you're interested, please go to this website to hear these and listen with headphones so you can test for yourself whether you hear the proper instruments sounding from the proper directions. Okay. So what you'll see when you go there are videos like this where the input is the top video and the monaural audio in black, and the output from our method is the spatialized sound, which here I'm showing in blue and red alongside the ground truth at the bottom. Okay, so here's one such clip. Okay, so here again, you're just seeing it, but if you listen with headphones, you'll hear that the drums are coming at you from the left, the piano's coming at you more from the right. And that's just inferred from the video alongside the monaural sound. And of course, we've quantified how well this is working against ground truth, both for the kind of data I just showed you, our fair play data set with a lot of musical instruments, as well as some even more challenging YouTube videos, which are the other three columns in this table. Which have music, tourist videos, street scenes, sports, and others. And across these, then, we're getting good results from this mono to binaural approach compared to other things you might do, including if you were to just copy the monaural sound twice and use that as the output. Okay. All right, so far I've talked about sound helping us understand the environment around us in a spatial way, both for visual echoes in terms of feature learning for RGB and RGB encoder, and then now just briefly about 2.5D visual sound to learn from video how to create immersive spatial sound, because the method tries to understand the link between the objects it sees and the sounds they may make. Now in this last bit, I want to continue talking about this ability to learn about a physical space about its geometry, materials, and where things are, but now in the context of navigation. And this is also work that we're presenting this week. We've presented in the main conference called Sound Spaces. And I'm going to be this is the work that introduced the simulator I mentioned earlier in the talk, but now I'm going to talk about it in the context of audiovisual navigation. So in navigation, there's a lot of exciting work happening in our community, looking at how you can train an agent to understand the world and its semantics and geometry such that it can make intelligent decisions about how to move around to find things. For example, an agent that could look at an RGB egocentric view like this and make smart decisions about where to turn or move next in order to find a telephone or to try and get to a specified destination further away in the scene. And I'm citing some of those methods down here at the bottom of the slide. What's really impressive is these are methods that are exploring really new forms of mapping to the point where agents can enter in new spaces they haven't seen before, and because of the geometric and semantic context, make smart decisions about where to go to get a complete map or to solve a navigation task. However, throughout this work, these agents have been deaf and the environments they walk around in have been silent. So with the sound spaces audio renderings that I introduced earlier in the talk, now we're able to change that. Now we can think about agents that live in lively sounding environments and who use those sounds to solve a task. In particular, we're interested in an agent that can navigate to a sounding source. So imagine the phone's ringing in another room. Can we have agents that have learned how to go find it efficiently? And what's really neat about having sound at our disposal is that means we can sense this kind of target or source even before we see it, right? So if I have my agent over here in the yellow and the phone is in some other room, it won't see any signal about where it might be just by looking yet. However, the sound is going to bleed out of the doorways of these rooms to indicate what would be the right way to go to try and get closer to this object. Okay, this is just an intuition of why sound is going to help us solve this navigation task and what we can expect from it even when we're far away from the object. So here I want to show you a sample then of what the audiovisual navigation task is like. And when I show you this video, it's both the visual and sound rendering from the Matterport environment, instrumented now with our Sound Spaces audio rendering. And the task is that the agent needs to find the smoke alarm. So it's going to hear it beeping, it's also going to hear a piano playing, and it's trying to get to where that target is. So here, let me play it for you now and listen as closely as you can. Okay, so I hope that you could hear how, first of all, there were a couple sounds going on. Second of all, they'll change in their intensity as we moved closer to them. If you to listen to this video from our website with headphones, you'll also hear the direction of those sounds as you move around. And furthermore, the agent needs to make this kind of navigation happen even without a map, right? So the map on the right is not given to the agent in this problem. Rather, it needs to build up this map through the visual input as it moves along. Okay, so those things are going to happen simultaneously, try to solve the navigation task while also building up this map of the new environment. So I can contrast then the task that we're introducing here with a more traditional task recently called point goal. So in point goal, the navigation task is the agent is told from the onset that the goal is at a certain displacement with respect to it, and it needs to navigate to that position. This is still non-trivial because the agent doesn't have a clear direct path to it. It still needs to see the environment and figure out where it can navigate in order to get to that final destination. However, in contrast, in the new task that we're studying here called audio goal, the agent is not told where the goal is, it just hears it. Okay, so this is, the phone's ringing somewhere, we don't know where, but your goal is to find it. And of course, we can put these together, so we also consider an audio point goal where the agent also gets a pointer, and so it can hear, get that pointer, and see. So to start modeling an approach for this, we put together...
Kristen, sorry to interrupt you, but we're at the 5-minute point.
Okay. All right. So sure. Do you mean 5 minutes including questions, or 5 minutes and then questions?
No. You still have 5 minutes, and then we'll have 5 minutes of questions.
Oh, okay, great. Okay. So here we're developing a deep reinforcement learning approach to train a policy for an agent to navigate to solve audio goal or audio point goal. And so it looks like this. On the input side, we have our eyes still, so we can see RGB and depth. But we also have audio, so we can hear from the left and right ear this binaural sound. And these are the spectrograms coming in as input. And finally, optionally, we have some GPS sensing to keep track of our own odometry and where that pointer to the goal. Now, from these inputs then, we'll train a deep reinforcement learning agent to choose actions. And these actions are going to be the choice of, do I turn left, do I turn right, do I go straight, do I stop? Okay, so at every time step, the agent's making such a choice, and it learns the best behavior, the best choices to make based on this loop back between the actions it chooses and how the environment reacts, both in terms of what it will see next, but also the reward that it's given. And the reward it's given is based on this navigation goal. So a big reward if it gets to that target destination, and incremental rewards every step that it's starting to get closer. Okay, so we're training up a policy that'll tell the agent how to move in order to solve this audio goal task. Now, importantly, we are very interested in this case where there is no point goal telling us where the goal is, and there is no GPS sensing. So in the results I'll show you shortly, we are going to consider the case where we have this point goal or GPS pointer and cases where we don't. We only have the eyes and the ears. So first, let me give you a sense of how audio is going to add to this navigation task. So if we first look at the point goal agent, one that's trained in just the same kind of format and architecture as I showed on the previous slide, but does not have audio sensing, then this agent trained for the point goal task is trying to find this ground truth shortest path down to the goal at the bottom in yellow, after starting at that blue square at the top. But in this particular instance has failed because it kind of started bobbling around in the same room. Why does it do that? Well, it's because there's a very strong pointer from the beginning saying that the goal is this at this displacement, so it's trying pretty hard to get down there and runs out of time before discovering the exit to the room. Now, this will lead to success rates like you see here in the table for the point goal agent. If instead we allow this agent to hear, then we start to realize that advantage I pointed to earlier in my talk with the sound bleeding through the doors, right? So because it can hear, now it ignores that strong inclination to go down only according to that point goal pointer, but finds its way out of the door to exit and then make a reasonably short path to get to the target. And that yields across the board much better accuracy for the success rates in navigation. Okay, so this is great. I mean, we would hope that if we add audio, things get only better, right? And they did. But here's what else happens. So what we know is that if we have agents that rely too heavily on perfect GPS sensing, they'll be in real trouble if GPS is not so clean. And so what this chart does is look at what happens as the GPS is corrupted increasingly as we move to the right. And we're looking at navigation success rate on the vertical axis. So the point goal agent in green will fall down, as can be expected once the GPS is too noisy on the right-hand side. However, the audio point goal agent that we were just looking at is fairly robust, can tolerate those changes because it too is suffering from the GPS corruption, but it has this audio spatial sensing on which to rely. Now take it one step further and think about that audio goal agent who does not have any point goal information at all. It's just relying on eyes and ears. So without GPS, certainly this agent is completely immune to any noise coming from the GPS. And this is exciting because this is a very realistic scenario to expect that in these indoor environments, the GPS will be noisy if not dropped. Furthermore, even if we add noise to the audio sensing to make a poor quality microphone in this simulation, then the success rate has moderate to negligible drop. Okay, so this is exciting. It means we now have agents that can answer this real world question of how to find things that are making some noise in an environment. And it also shows how audio is stepping in as an important player for spatial sensing. And in fact, in this last slide, I'll show how if we look at the features that are learned within that navigation pipeline that I showed earlier, the features that are learned for the sound input are on their own starting to code for the very factors you want in order to solve the navigation task about space. So in these two t-SNE plots, we're looking at 2D projections from the CNN learned features. And what's cool is that these are color-coded according to distance to the goal on the left and angle to the goal on the right. And so the more these colors cluster together, it means that the features are representing this to the agent. So in other words, from blue to red is that the goal is close or far, and that the goal is to the left or to the right. And this is coming out without us expressing it explicitly. The agent's learning it from its own audio sensing. Okay, so I'll conclude here. I've talked about how we can do new things for spatial understanding with audio and visual inputs. The key ideas were this new rendering environment for Matterport and Replica that's compatible with Habitat, the ideas for visual echoes, 2.5D visual sound, and now this audio goal navigation challenge. And I want to thank you for your attention and would be really glad to have any comments or questions.
Thank you so much, Kristen. This was great. Let me read you some questions from the Q&A. I think we have time for 1 or 2 questions, and then we'll continue. So the first question is from yeah, and anonymous, I guess. And the question is, are the echo inputs processed as images or audio sequences?
Yeah, the echo inputs are processed as spectrograms, and at that point, yes, you can think of them as images, and that we're using CNNs with basic architectures on top of those spectrograms.
Thank you. And there's another question from Brent Griffin. And Brent, sorry, let me quickly summarize this. That's a bit long. Okay, yeah, Brent is essentially asking, humans have only 2 years, and that's great to mimic 2 years in a simulator, but a robot is not necessarily limited to just 2 years. And have you considered adding some more microphones with different offsets, and can this further improve the performance? I hope,
Yeah.
Brent, I did justice with your question.
Yeah, for sure. It's an important point. We've stuck with binaural in these results really just to allow us and to hear what's happening and to get intuitions about the results. But we aren't restricted to it, and neither is the simulator. So you could render ambisonic sound and hear from that richer signal. And we've done this with some of our results, say for navigation, as you'd expect, it gives you even a richer sound input.
Thank you so much, Kristen. This has been great. And there are a few more questions. If you want to check them out in the Q&A, you can type the answers offline, and we'll pass the mic to Srinath to introduce our next speaker. Thank you again, Kristen.
Great, thank you.
Thank you, Kristen. And before I introduce the next speaker, I just wanted to quickly point, I'm just going to share my screen so that I can point you all to the interactive session of the workshop, which is happening on an interactive website called gather.town. So the link to this is on the screen. And this interactive session has both a virtual ballroom and a poster session. So if you want to hang out there during the workshop, you are most welcome to do that. And I will post the link to that on the chat window as well. All right, so with that, it's my great pleasure to introduce our next speaker, Angju Kanazawa. Angju is an assistant professor in the EECS department at UC Berkeley. She is also a research scientist at Google Research and has previously spent time at the Max Planck Institute for Intelligent Systems and the University of Maryland at College Park. Her research is at the intersection of computer vision, graphics, and machine learning, focusing on 3D reconstruction of deformable objects such as humans and animals from everyday photographs and video. And today she'll be talking about learning morphable shape models from image collections. Angju, as usual, I will give you a warning at the 20-minute mark, but other than that, the stage is all yours.
All right, thank you so much. Can you hear me?
Yep.
All right, great. Thanks for the introduction. All right, today I'm very excited to talk about learning 3D morphable models from image collections. But really, I guess I don't have to reiterate this message to the people of this audience, but I want to express again that 3D is super fun and you get to do a lot of cool things like reconstructing yourself. So this is one of the work that we presented in ECCV that uses implicit functions to reconstruct 3D human shape and appearance from a single image. But today I want to talk a little bit more about general non-rigid objects. And in doing so, I want to set forth this premise, which underlines much of my work, which is that we live in a world that is three-dimensional and dynamic, full of life with humans and animals interacting with the environment and each other. And in doing so, these objects or humans or these agents that are moving around interact with the world by deforming their bodies. And the state of the body can reflect a lot of their internal states as well as their activities, what they might going to do. Here's another picture of a cat that is using its body to hunt. And in all of these instances, these objects take a particular different shape because they deform as they move around. And this is why capturing the deformation of these objects is directly related to understanding their intent and their action in the world, which I think is quite interesting, exciting. And so much of my work revolves around recovering non-rigid 3D objects from images and videos, such as humans and animals. More recently, we have this work on humans and objects. Once you can reconstruct animals from images, this work uses some level of manual annotation, but we can reconstruct this white rhino, which is almost going extinct. And then we can 3D print it. If you can reconstruct humans from video, you can also use that to train a policy or a virtual agent that can imitate or learn to execute those skills as seen in video, not just copying over the animation, but to actually physically animate in this environment and do all sorts of cool things. Of course, there's a lot of potential in content creation if you could recover 3D from images and allow such tools to be accessible to everybody. Now, there has been lots of progress in 3D human perception. Here, I'm just showing the videos I have, but there's been a lot of other really cool work, and there's been so much progress in this area in the past few years. It's just very exciting. But much of the progress in humans are thanks to due to a large amount of available 2D and 3D supervision. So 2D labels, of course, but what is key in a lot of these works is that we have scanned lots of people in various different shapes and forms, poses. And what this data is useful for is that you can use this to create a morphable model of human bodies, as shown here. This is from Michael Black's lab, which a lot of us use. And now the question is, for humans, you have all of this 3D data, so you can learn this. But what are you going to do for other objects or other animals when such scan is not possible? So that is the focus of today's, what I want to talk about today. How can we learn a similar morphable model without 3D supervision? And how do we reduce the amount of the 2D supervision that is required in order to do this? Okay, so to recap, the reason why animals are hard to capture at large scale is because they don't listen to you and they run away like this, which means there isn't that many 3D ground truths, especially at large. Now, there are multiple, I want to recover this multiple settings of multiple images or how you might recover 3D shapes. So if there's no motion, if the object doesn't move, you can take a video around the object or take multiple pictures and reconstruct the shape, as shown in traditional approaches or also learning-based approaches. But these approaches are restricted to rigid objects. If the objects are non-rigid, then every single time you look at it, the instances might have changed because they move around. And so the situation is a lot closer to a situation where, you know, you take a picture, you look at it, and then it's this one bird, but then when you look at it again, it has moved around. And then maybe there's another bird that comes in and it comes into your picture. So the setting that I want to focus today is in this setting, which I believe is the more in the wild and appropriate for non-rigid object setting. Okay, but before talking about this, I do want to cover the general paradigm for recovering non-rigid 3D shape from images. And it goes like this. First, you learn a morphable model from 3D data, and then two, you fit the model to images. So let's look at some classic examples. So this seminal work from Blanz and Vetter learns a morphable model from 3D data using this large scans of faces. And then now this has like a control parameters that you can, you know, use to change the faces. And now you can actually fit that model to images using some kind of differentiable rendering or some optimization. Same goes with humans. We have a morphable model from large scale of 3D data. Michael Black's lab has built this really nice model. And with a kinematic tree, you can model articulation under this model. And then again, we fit this model to images. Over here in this particular example, we use automatically detected 2D key points to minimize the reprojection error in order to do this. I'm going to give you another example. This is okay, right. So if you have lots of data like this, you can also learn to predict this instead of optimization, which is much of the work that goes on right now. Okay, I'm going to give you one more example to kind of show you this pattern. In 2017, Michael and Sylvia and Michael and I, we collected, scanned these toy animals that are for kids' toys, like 30 or so, and then we made this morphable model which spans this space of 4 quadruped families. And yet again, now you can fit this to data and then reconstruct the shapes as well as texture if you had multiple instances. Okay, so I hope this paradigm is clear and the importance of the morphable model. Now, the question is, what if you don't have lots of 3D data where you can't actually learn this morphable model? So today I want to talk about the hybrid approach, which learns the morphable 3D model from image collection without 3D while you're actually trying to fit the data at the same time. So this is the work that we presented in ECCV 2018 with Shubham, Alyosha, and Jitendra. So the goal over here, to reiterate, is that we want to learn a 3D deformable shape model from 2D information. By 2D information, I mean images, a set of key points, semantic key points, and silhouettes. But we don't get to see any ground truth 3D bird shapes. Okay. And so how do we do this is because the idea is that during training, we will look at many instances of the birds, learn what bird shapes are like, learn the model, and also learn to predict the model, so that at test time, when you see a new images of a bird, you can use this knowledge in order to recover both the shape and the appearance of this bird. Okay, but we don't have ground truth 3D. So how do you actually go about this? And the key idea is to take advantage of the underlying 3D inductive bias or the image formulation in how a picture is being formed. So whenever you see a photograph, this is made by taking a picture of an existing 3D instance, which may have some kind of appearance, which you may, for the moment, think of it as a clothing. And then if you take a picture of this bird from a different view, you'll give rise to different viewpoint. Now you can change the appearances, the same thing. And you can also change the pose, as well as shape, as well as the appearances, and obtain different kinds of bird images. Okay, so we take advantage of this factorization structure and follow this concept of analysis by synthesis, where the idea is disentangle the image into these 3D factors: camera, shape, and texture, such that when composed together, it can reconstruct the original input image. So you can instantiate this with a convolutional neural network. You can have it output the camera and the shape, texture, pass it through a differentiable renderer, and one of the main objectives is to ask if the reconstructed image matches the input image. Okay, but earlier in the work, in the talk, I explained that this particular work requires 2D key points. So why do we need 2D key points? So we really need the 2D key points to ground the camera where the viewpoint of how we're seeing each bird. So what we do is we use the key points as correspondences and pretend like as if all the bird images come from a single bird, even though they're not, and then use the correspondences as use the key points as correspondences to solve a structure for motion problem, which gives you a very coarse shape, as well as the viewpoints for each images which you're looking at this image, looking at each image. Okay. And then after solving this SFM on these key points, for every image, you basically have a pseudo ground truth viewpoint of which direction you are most likely looking at this canonical bird. So in this work, what we do is, in order to train this model, we use that key point and the camera coming from the key point to ground the solution. So what we do is we apply losses where the predicted camera should match that of the SFM camera. And we also have some key point learning process on top of the mesh so that the key point is reprojected. That's not really that important. The important thing is on the left. And then you also have this texture loss, image reconstruction loss through the differentiable renderer, as well as this mask reprojection loss. Okay, all right. When it comes to 3D representation, which is the topic of this workshop, well, in this work, we used a mesh combined with a traditional linear morphable model. So given this image, the final 3D shape, which consists of n vertices of a mesh that comes from a sphere topologically, is formed by a single average mean shape of a bird, which is shared across the entire category for all birds, as well as this per vertex shape, per vertex offset that is going to be outputted by the network, which is a shape deformation. Okay, so this is instance specific. You take an image, and for every single image, you predict how each vertex needs to move around in order to represent the shape of that particular bird. Okay, so this is reminiscent of early 3D morphable models that you've seen in Blanz and Vetter, like those face models, but learned without any 3D data. For texturing, one nice thing about mesh is that you can take advantage of the UV image structure that is often used by artists. Here, the idea is that every 3D object, you can unwrap its surface into a two-dimensional space, which forms an image, just like the Santa. So given two birds, they are both deformations from a mean bird, and the mean bird is homeomorphic to a sphere. And the sphere we know how to unwrap, which we do a very simple spherical coordinates, which gives you this UV mapping. And so whenever you color this UV image, you can color the sphere, and you can color the mean bird, and you can also color all of the birds that's coming behind. So this allows you to use some kind of convolution neural network to predict the image, the UV image from a single input. Of course, this is still extremely an underdetermined problem, so you need some regularization, such as that the surface needs to be smooth. One nice thing about the mesh is that it's easy to incorporate such kind of regularization. We also bake in bilateral symmetry in the vertices of the bird. Okay, so with that, you can train this, and so you get some kind of results like this, where you can see that the model has learned slightly different shapes of the tail, like longer and shorter. We've also run this on other categories. And then another nice thing about these factorized representation is that you can swap these textures. Okay, all right, so that's all good. And so this really takes a, takes a step towards scalable 3D learning from images. Now, I want to talk about this new work that we are presenting at this ECCV, because that's nice, but the problem about all of these approaches is that you need all these key points. How can we get rid of these key points? So this is the focus of the work that is being presented at this ECCV. And unfortunately, actually, the poster session is going on as we speak, overlaps. So if you have any questions, please copy this URL. And after this talk, you can ask a lot of questions to Shubham, who is the first author of this work. All right, so a lot of work require key points. And why do you need to use key points? Or what's the problem with the key points? The problem with the key point is that it's very time consuming to obtain them. For every single image, you have to go and click them. There are a lot of interesting work that tries to search for, tries to learn automatic key points. And there's been lots of interesting progress in this area. However, these approaches tend to be view dependent, meaning that if it could identify left wrist and the right wrist, everything on the left side of the image is always going to be the left image, even if it was people moving around, and even if it was actually right side, it will still say to the left is left. And so they're not 100% 3D yet, and which makes it it's not for the entire sphere. So which we still can't use these approaches. So we can't yet now rely on key points for free. So in this work, we get rid of key points, and while we get rid of key points, we still need silhouettes. And instead of getting rid of key points, we actually bring about this single initial template shape that we need to start this process. And it's like replacing a per instance image annotation with a single template that is used in this work. Okay. All right, so let's just review why we needed the key points. We needed the key points to identify the camera viewpoint for each image using SFM, and then we use it as a camera loss. So let's just go back and then revisit this model. What if you just didn't have any camera as a supervision? You just get rid of the SFM camera supervision. Then what happens is that when you train a model like this way, this is the output of the model, which from one view it looks okay, but when you look at it the other view, you notice that it's completely flat and it has learned a degenerate shape. And this is because when there's no camera supervision, the initially predicted cameras are all garbage, and when the camera is bad, the shape compensates to fit the bad camera, which causes more bad camera, and this puts you into this cycle of local minima. In particular, one thing that we noticed was that searching for the camera is a lot harder than adjusting for the shape, and so the models tend to always adjust the shape compensate for the error that way instead of moving around the camera. So in this work, what we propose to do is, instead of predicting the camera, which is a quite challenging problem, and especially because in the beginning you may have multiple camera hypotheses that you want to consider, we get rid of this camera prediction branch, and instead of predicting, we optimize the camera during the training. By that, what I mean is that for every single instance, we're going to instantiate this thing called camera multiplex, which is just a set of camera hypotheses for each image. Okay, so every single image gets k possible camera explanations. Another different image will get a different camera explanations, and we will just keep them around. So this is similar to particle filtering, except there's not that much of the resampling stage. So we initialize this camera multiplex using the template shape. This is why we need the template shape. So what we do is we take some template shape of this category and then search for the camera viewpoint that minimizes the silhouette loss. So here are 3 different viewpoints that equally minimize the silhouette reprojection, also highlighting the challenge of this problem, meaning that there are multiple viewpoints that can minimize the silhouette loss. Okay, this is why we need the template shape, because if the template shape was completely spherical, then every single view would be likely. Okay, so the way you train is you take an image, you predict the shape and the texture using the same parameterization, same representation. Now, instead of predicting the camera, we're going to look up our database. It's just a key value thing for every single image. You pick up the possible camera hypotheses. And for every camera, we render the shape and the appearance of the bird from each view. Now we can compute some loss for every single camera or rendered image, and then we can convert this loss into a probability through a soft min. And then we can take the expected loss in order to update the shape and the texture. So to be more specific, what we do is for every single camera, the loss is, again, these reconstruction losses. How well do you explain the texture and the mask? And every single camera is updated to minimize this texture. So you also update the camera multiplex that you're storing. It's just a key value pair of variables in PyTorch that you can actually update. Right? So it's very similar to kind of another gradient updates. And for the shape and texture, you take the expected loss using the soft min to convert every single camera into probability, and then you backprop against this expectation for each shape. Okay, so along with the other regularizations. So now, after training convergence for shape and texture, now you can actually identify the most probable camera in your camera multiplex for each instance, meaning the one that minimizes the loss the most. And then you can use that to train a feed-forward camera predictor. So you optimize and you predict. So this way, at test time, even though you weren't jointly predicting the shape and appearance at the same time, at the end of the day, you can still have models that can predict both the camera viewpoint, the shape, and the appearance from a single image. Okay, so here are some results, qualitative results on the bird data set. So this is a result obtaining without key points. And so now we can quantitatively evaluate this. So here we show the camera distribution of the birds on test data using the structure for motion camera. So on the x-axis, we have the azimuth, and on the y-axis, we have the elevation. So we have all the viewpoints of all the test images, and we are wrapping it into 2D plane. And so when you predict the camera, you want your camera distribution to somewhat look similarly to this. So here is the results from the previous work that we talked about, which had supervision by the SFM camera. So it was basically trained with the SFM camera. That model can recover distribution that looks quite reasonable. Now, if you train the CMR without any key points, meaning without any camera prediction, camera supervision, and just naively train a CMR, you notice that it got flat, and you see the collapse of the camera as well. Now we also took the canonical surface mapping paper, which also doesn't use camera key point supervision, and it's better than naive CMR, but you still see some collapse. Okay, and this is our approach with the camera multiplex, which obtains distributions that's a lot more like the ground truth distribution. Okay.
I'm just sorry to interrupt. Just wanted to let you know that 5 minutes remain.
Sorry, okay. Sorry, I got scared. Okay, that's good because I'm almost done. All right. Okay, so here's some numbers, and so you can see that different approaches. So the unsupervised baseline, there's CSM and CMR in terms of this quality of the camera. And the thing on the right is our UCMR. But the interesting thing over here is if we don't predict the appearances, our camera is not as good because the silhouette alone is still ambiguous to figure out which direction you're looking at the birds. So this kind of tells you that the image reconstruction loss through the texture prediction is quite important for figuring out the right camera and therefore better shape. Okay. All right, so here's some more results. So we run it on different categories, such as motorcycles, cars. And now that we can run it on images without key points, we also collected this new data set of shoes, and we reconstructed shoes. Now, like I said, the most interesting about these approaches is that you are learning a morphable model or a deformation of each category. And so here we show the interpolation. So we run PCA on all of the recovered shape, and here we're showing an interpolation of it. So with the birds, it's learning different shapes of the head and the tail. With the cars, it's learning these different the wheel types. With the bike, you also learn these different types of shapes. And you also see subtle kind of differences in the shoes. We notice that the shoes itself does not as deform as much in this particular data set. Okay. And here's an example. Here's comparing the initial template shape and the learned mean shape, the final converged shape. So you initialize something, the final shape is something different. So there's some differences. This is a visualization of the space of predicted textures. So we output these UV images, and now you can run PCA on that also, which shows that the kind of texture variation that happens in this data set, which is like blue birds and the green birds and birds with like black markings on the face and different markings on the body and the belly. And so that's kind of cute to see. Yeah. All right. So I do want to mention that there's a very, very recent work that just came out on arXiv this past July. And this approach really takes these mesh representations to implicit functions. So they're quite similar, especially if you're sticking to the sphere topology. So instead of having these explicit vertices, you can have an implicit function that can predict where the points are for every single point on the sphere. And using this, you can similarly learn CMR like a shape deformation basis. And using this, Shubham, this work also doesn't use key points and can be applied to all these very cool animal models. And it can reconstruct these elephants and giraffes, which is super cool. So that's a really nice, connection with all these other different representation. It's nice to know that you can still learn different deformations using different representations. Anyway, so the takeaway of this work is that good camera is quite key in learning good shape 3D model from images. And instead of predicting camera, which tends to be really difficult, hedge bets by keeping multiple possible cameras and move them around, a little bit similar to particle filter optimization. And now that we can reduce supervision even more without 2D key points, there's more possibilities for learning 3D from images. All right. I think with that, I want to thank my students and collaborators for this work, and thank you for your attention.
Thanks a lot for the great talk, Anju. As we wait for attendees to ask more questions, please type in your questions in the QA box if you have questions for Anju. And while our attendees type those questions, I had a couple of questions that I thought I should ask. So one question, Anju, you showed some results of shape variation or the space of shape variation of the models that you learn. Do you have a sense of quantifying how much shape and texture variation you can capture using such self-supervised or unsupervised techniques?
I see. Well, yeah, this is kind. You can if well, so if you had 3D shapes, then you can use the reconstruction by these PCA bases to see how much of it it's really capturing. In this case, it's kind of difficult because we don't have the ground truth 3D shapes. That is an interesting question. I guess we can be looking at some reconstruction metric on the images, but actually, it's not something we kind of try to quantify. But that's a good question. Yeah.
Great, thanks. We have a question from one of the attendees. Davis Remper asks, in the shape at viewpoint without key points work, do you still enforce symmetry on the reconstruction? If so, how important is this for good results? How might you approach non-symmetric objects like animals with lifted legs?
Yeah, so these approaches, these methods all enforce symmetry. I want to be careful. This is something that is good to ask to Shivam at the poster session. The way we enforce symmetry might be slightly different from CMR. I think it's the texture is not. Yeah, shape is always with the baked in symmetry. And the reason why we included the symmetry to begin with in CMR is, well, A, because symmetry is a very reasonable regularization, but B, it doesn't break if you get rid of the symmetry. But for example, it would suffer a lot from the foreshortening effect. So that's one of the reasons why we are including this. Yeah.
Great, thanks. We have time, maybe 1 or 2 more minutes if someone has another question. Okay, let me ask another question. So one question I had was in many of the examples that you showed, the shapes are kind of organic. So they're animals, birds, and other animals, and so on. How do you think your approaches would work for articulating objects like, I don't know, like doors or robotic arms, which have like rigid articulated parts?
Yeah, that's a really good question. I think traditionally, yeah, the morphable models have been a linear model. And so you only want to use it to model things that are linear. And by this, I think an intuition that my advisor tells me that I really like is that if you take two shapes and if you look at the linear combination of it, is this still a valid shapes? And for articulation, this is actually not always the case. And so this is why morphable models of humans, for example, have a kinematic tree that can actually model that independently. Yeah, but the interesting thing is it's not like you can't, because technically, if you pass things through a deep network, it's not a linear model. There's some nonlinearity involved. So this is why in this work with the Shivams, I don't think there's. I think the implicit functions are also learning slightly. It's kind of learning both the shape and the articulation changes. So that's quite interesting. So I want to learn a little bit more and read more into this. But yeah, so the model can actually capture. At the same time, I think there is some benefits to factorizing shape and pose, because that also gives you more control. And one nice thing about, modeling pose as some kind of kinematic tree is that it gives you more control, or gives you more this low dimensional representation of the state of the object. And these are kind of things that might be useful if you wanted to use this for not the graphics tasks, but more for like robotics based tasks, like, understanding where their arms are and such things like this. Volumetric models may not always have that kind of representation. So that's, really the pros and cons of these different approaches. Like this work that I had first in the beginning, that can reconstruct this like shape and the appearance, this implicit function-based work can capture these really crazy like skirts and stuff, which is difficult. I mean, skirts are difficult. We're making, I think this is quite, this is a progress over here, but these approaches, you don't have any of these high level control parameters. So then it might be difficult to use it. These are still kind of surfaces, which you can't understand. So yeah, somewhere in between that, I think is good. And I think there are actually some recent work that combines kinematic tree with the shape. Now, how do you learn these kinematic trees or articulation from data? I think that's a really interesting question. That's relatively underexplored.
Great. Thank you so much for that. All right. So thank you so much, Angju, for your talk and for answering our questions. Next, we move on to the poster session. We are running a little bit behind schedule, and therefore, I think we will reconvene in 1 hour for the poster session. And I'm going to hand the stage back to Or so that he can tell you a little bit more about how the interactive poster session is going to work.
Thanks, Andrew, for the great talk, and thanks, Rina. So we're about to start the poster session. I've already visited Gather.town and seen a bunch of you trying out the platform. I hope you're liking it. I know there are some technical issues with the live stream. We're going to try and figure that out now. Yeah, thanks for sharing the screen. This is very helpful. This is the link to Gather to visit the poster session. If you want, the presenters are already standing, or most of them are standing next to their podiums. So go to the colored regions and interact with them, ask them questions. If you want some information about which posters are presented, you can visit this link. So I just posted 2 links to all panels, and so you could all see. You can click the second link to see which posters interest you most. Yeah, just enjoy your time on Gather, and we will still keep track of this chat. So if there are any issues, please post them here, and we'll track them and try to solve them. And we'll reconvene in 1 hour. So that's 6:30 PST time.
Right, and just as a reminder, we are running 15 minutes behind schedule. And as Or mentioned, we will reconvene in exactly 1 hour. And meanwhile, in this Zoom session, we are going to keep this running, and we are going to be playing all the posters, the videos of all the posters live in this Zoom session. So I'm going to start playing that for you. If you have any technical difficulties, either with Gather or with the Zoom webinar, please feel free to send us a chat either on the Zoom webinar or on the Gather chat session. Okay, the poster session video is going to start playing now.
Hi, I'm Philip, and I will introduce you to our work on 3D texture synthesis, namely learning a neural 3D texture space from 2D exemplars. For a given texture exemplar set, the goal of our work is to synthesize them. Such exemplars can be casually captured using a mobile phone. Prior works have been focusing on synthesizing single exemplars, but did not focus on creating a space of textures, whereas we do. Having a compact space of textures allows us to synthesize textures beyond the given dataset. However, the main contribution of our work is the synthesis of 2D textures, using only 2D textures as input. Having said that, there are a few more properties that our method enjoys. First, our method is able to produce diverse outputs given a single exemplar.
There is a cluster of people
and can also output textures of arbitrary size.
You see them just randomly discuss something.
We create a smooth
I think we don't need to stay at our host area, maybe.
Between exemplars. The synthesized texture can be sampled at any arbitrary resolution, which allows for zooming.
Yes.
A very important feature is computational efficiency. We can synthesize textures pointwise, which makes our method lightweight and efficient. Lastly, our work allows for 3D texturing, independent of shape and resolution. Let's have a look at our method. We are given an exemplar set Y. At each training step, a crop of a single exemplar is taken and encoded using an encoder G. The encoder G returns Z, which represents our compact latent space. Our latent space is then divided into 2 parts using a translator module H. It outputs a texture code E and a vector of learned transformations T. The texture code E can be seen as what kind of wood or grass is encoded. The vector of T's, on the other hand, is used to transform the coordinates before reading the noise that we're sampling from in the next step. Therefore, the noise function takes as input a coordinate x, the vector of transformation matrices T, and the random seed psi. Before we have a look at the noise function, let's dive a bit more into the translator function and its purpose. The translator allows for Z to be more compact as it takes care of operations that would have to be repeated for Z, but are the same for all x. In this example, a translator lifts Z from 3 to 8 degrees of freedom, or in other words, two 2x2 transformation matrices with 8 degrees of freedom are parameterized by 3 parameters. Getting back to our architecture, the next step is to sample noise. Let's have a closer look. We sample noise at different frequencies. The first level produces a low frequency noise image, whereas the following levels increase the frequency. This is achieved through scaling the coordinates by different predefined factors. After applying the given transformation matrix from the translator function, we sample noise. Now we finally get to synthesize our texture. We feed stacked noise values for each sample location combined with the texture code E into a learned function f that returns a single color value. Note, during training we sample neighboring points in form of patches in order to apply statistical loss. In particular, we feed both the cropped input patch and our output patch
to a bit weird here. So people just randomly working
of the VGG features. On a more high-level view at this architecture, we can see that the
yes, but I see no noise in their
and the random
position.
allow us to control the synthesis of our texture.
Randomly
we refer to
run.
the encapsulated block as the sample function S. If we only change latent code Z and keep everything else fixed, we will get different texture variations, whereas if we keep Z fixed and change X or Xi, our method will produce different variations of the same texture. The only question that remains is, how do we synthesize 3D textures if we have only 2D textures given? The answer is very simple. Instead of sampling a 2D position, we sample a position in 3D. For training, that means we randomly extract 2D slices along the 3 major axes and ask for the slice to be statistically correct according to VGG. We conclude that our method creates a compact space of textures, is computationally efficient, and allows for 3D texturing. Additionally, it creates diverse textures by design. However, our work also comes with limitations. So far, we can only handle stochastic, non-stationary textures. Eventually, we would like to produce BRDF textures instead of just RGB ones. Hence, the question arises, would it be possible to learn BRDF textures from flash images? Well, here's a glimpse of what this could look like. Further results and experiments are available online as well as code. If you have any questions regarding our work, please feel free to reach out to me. Thank you for listening. Hi, I'm Philip, and I will introduce you to our work on 3D texture synthesis, namely learning a neural 3D texture space from 2D exemplars. For a given texture exemplar set, the goal of our work is to synthesize them. Such exemplars can be casually captured using a mobile phone. Prior works have been focusing on synthesizing single exemplars, but did not focus on creating a space of textures in order to apply instead of from flash images. Well, here's a glimpse of what this could look like. Thank you for listening.
We present BSPNet, a network that generates compact meshes via binary space partitioning. Recently, several methods have been proposed to represent 3D shapes within neural networks. These approaches mainly fall into two categories. One is to warp a template mesh into a target shape. Another is to represent geometry via implicit functions. However, implicit methods require matching cubes to extract the surface mesh. The extracted meshes are not compact and contain too many polygons. In this example, we show a 3D object generated by MNet. The mesh is obtained by running matching cubes at a resolution of 256, and it contains hundreds of thousands of vertices and triangles. We would prefer to have a compact output mesh with a few hundred vertices and retain the ability to represent complex structures. To address these problems, we propose a neural network which outputs meshes natively. Our generated meshes are low poly and guaranteed to be watertight. The edges can reproduce sharp details, yet can still approximate curved boundaries. Overall, we attain high visual quality with very few primitives, as reflected by the wireframe. Our key idea is derived from binary space partitioning trees. Given a set of oriented planes, and the connections to group them, we can compute the intersection within each group to obtain convex shapes, and then take their union to construct the final output. The entire process is based on CSG operations, hence the output shape is a polygonal mesh. We designed the network in such a way that each component represents a part of the BSP tree. Given a voxel model or an image as input, we use an encoder to get the corresponding feature code, and then use an MRP to map the feature code to plane parameters. The planes are the leaf nodes in the BSP tree. Similar to the training of other implicit models, we sample a set of points in space. The product of the plane parameters and the point coordinates will give us the sign distances, which are visualized in the first layer of the right figure. To represent the connections in the BSP tree, we employ a trainable binary matrix. The product of this matrix with the distances represents convex shapes. Finally, we introduce some auxiliary weights and use the weighted sum to approximate the mean pooling operation, or use mean pooling directly to obtain the final output shape. Here, we visualize the training process for a 2D toy example. We initialize the network with random weights before training, including the binary matrix that connects planes to convexes, and the auxiliary weights that aggregate the convexes to form the output. All weights are float numbers, so that the gradients can easily propagate. In stage 1, we train the network with reconstruction loss, and 2 other losses to help structure the tree. Note how the connections are changed in the bottom level. The first stage gives a reconstruction of the target shape, but it might not be accurate due to the continuous weights. Therefore, in the second stage, we binarize the connection weights via thresholding, and replace the weighted sum with mean pooling. Here, we show the input shapes in our 2D toy experiment. The task of the network is to reconstruct each image as a combination of convex parts. And here are the outputs. Since all shapes share the same set of convexes and tree connections, we find shape segmentations and correspondences in the convex level. Here, we show that the nth convex consistently represents the same part. We compare our method with several other methods that perform shape decomposition via reconstruction. Our method not only achieves better reconstruction quality, but also has better segmentation results. Similar to the 2D case, we can find natural correspondences between convexes. Here, we manually group convexes into semantic parts, and visualize correspondences using different colors. Finally, since our BSPNet is a differentiable 3D decoder, we can easily pair it with an image encoder to achieve single-view reconstruction. We compare with several state-of-the-art methods to show the representation ability of our network and the compactness of the outputs. Please pay attention to the close-ups of mesh tessellations in the middle. Our method achieves comparable performance to the state-of-the-arts while using fewer amount of vertices and triangles. There is a recent work, CVXNet, that also performs convex decomposition. Our method differs from theirs, as we target low-poly reconstruction, and our network has a dynamic number of convexes for different shapes. The source code of our work is available on GitHub. Thank you for watching.
Hi, I'm Song Yu, and I'm excited to present convolutional occupancy networks. This is a joint work with Michael, Lars, Mark, and Andreas. The question we are asking in this work is, how can we reconstruct large-scale scenes with the implicit representations? Our main idea is to exploit the nice property of convolution operations. Given some kind of input, for example a sparse and noisy point cloud of a shape, we define a 2D feature plane. In this case, it's the ground plane. The feature for a particular pixel on the plane is acquired by aggregating features of those points within this column using a point net encoder. From this process, we now have a local information on the 2D feature plane. And then we use a 2D UNet to further process the feature plane, which integrates the inductive biases into the model. After having the processed feature plane, we can now query the feature at every 3D point in the space using bilinear interpolation in this 2D canonical feature plane. Now, because we have a feature with richer local information for every query point, we only require a shallow network to take in a 3D location and its feature, and then predict the occupancy. We can also do the feature encodings for multiple canonical planes, for example the plane in X, Y, and Z direction. Now the final feature for point P is simply the sum of the features queried from these 3 feature planes. In addition to projecting into canonical planes, we can also use a volumetric representation and encode the local information into the volumetric space, as shown in the red box here. We then have a 3D UNet that operates on this 3D coarse representation, and we again have a readout unit in the form of a shallow occupancy network. But in order to obtain features for particular locations, we now query the feature from adjacent voxels using trilinear interpolation. Here is the direct comparison between the occupancy network on the top and our convolutional method on the bottom. We can see for our method, the features are not a global code anymore, but they are distributed in 3D space. They can benefit from the translational equivariance of either 2D or 3D convolutional networks. Moreover, since the features of our method have richer local information, we only require a shallow, fully connected network. Let's now look at some results. We first want to see if our convolutional method can also improve the quality of object-level reconstruction. It turns out this is indeed the case, in particular for objects with complicated shapes. Our input could either be a noisy point cloud or a coarse voxelization of an object. We can see the original occupancy networks lose quite some details, whereas our convolutional models here preserve much more details. Now let's look at the results on scene level reconstruction. We first generate a synthetic room dataset using ShapeNet objects. We train and evaluate on this dataset, and the input is a noisy point cloud. We can see that the occupancy network produces smooth results, but fails on recovering details. The other baseline method, screen Poisson surface reconstruction, leads to very noisy reconstructions. And our method produces detailed and smooth 3D reconstructions. We can also take the model trained on synthetic rooms and evaluate on the real-world ScanNet dataset, and the results illustrate that our model can generalize from synthetic to real data. We also test on very large scenes. Because we have a fully convolutional model, we can scale this to scenes as large as multiple 3D dataset. We trained on small crops from our synthetic room dataset and evaluate on such a large scene in the sliding window manner. This fully convolutional approach can scale to any scene because we can load sliding window into memories as we desire, and then erase them once processed. The results are then stitched together. On the right is a fly-through video for a reconstruction of a 2-floor building in the multiple 3D dataset. As we can see, our method is able to reconstruct such large-scale indoor scene with fine details by training only on synthetic crops. More information, including code and data, can be found in our project page. Thank you.
Hi everyone. Welcome to my talk on geometric priors of neural networks. Today, I'll be discussing the results of 3 of my recent papers on surface reconstruction from points. The problem of surface reconstruction can be summarized in the following cartoon. Given the black dots, sampled with noise from the dotted line, and possibly normals at those dots, we'd like to recover a discrete representation of the underlying surface. This is an ill-posed problem, since there are an infinite number of interpolating curves for the input points. Here you see two of them, the blue and red lines. At the core of the reconstruction problem is the choice of surface representation. Recently, neural networks have emerged as a powerful representation for surfaces in reconstruction tasks. Broadly, prior work has used neural networks in several ways. First, a neural network can predict a set of dense points on a surface from a set of sparse input points. These points can then be connected with off-the-shelf tools to recover, for example, a triangle mesh. Neural implicit methods have used a neural network to represent a scalar function in 3D space whose zero-level set corresponds to a surface. And atlas techniques have used neural networks as parametric charts mapping points in the plane to points in 3D. Here, the colored lines represent different parametric patches. In this talk, we'll focus on two methods in the latter two categories. Deep geometric prior for surface reconstruction is an atlas method. It was one of the first techniques to show that the inductive bias of neural networks leads to the surface reconstruction problem. The method works in 3 steps. First, given an input point cloud acquired from a scan, the method chooses neighborhoods. It does this by choosing seed points, which are a fixed distance apart, and considering all points within a ball of radius r around those seeds. Then, for each neighborhood, the method fits an MLP, mapping points in the plane to points in 3D. The points in the plane come from a 2D distribution, which can be adapted during fitting. The MLPs are trained so that the 3D lifted points match the input points within the neighborhood. Since we don't have correspondences between the lifted and input points, we use an optimal transport loss, which jointly fits geometry as well as correspondences. The result is a set of local parametric charts, which overlap, and point-wise correspondences between those charts. Using these correspondences, we do a global fitting phase, which encourages the charts to agree on overlapping regions. Finally, we use the charts to generate a dense point cloud, which can be meshed using off-the-shelf techniques such as Poisson surface reconstruction. Remarkably, we see that within a single patch, the parametrization has low distortion, the surface does not oscillate, and we also recover sharp features. We ran our method on a standard benchmark and quantitatively outperformed the state-of-the-art. Finally, while existing techniques often trade off robustness to noise with the ability to represent sharp features, we find that our method is capable of both. Deep geometric prior shows that the inductive bias of neural networks leads to high-quality reconstructions, which can capture sharp features and are also robust to noise. That said, our method requires one network per patch and is quite slow. It also requires some parameter tuning to select the size of patch neighborhoods.
Hi, I'm Lior, and I will present to you our recent work on multi-view neural surface reconstruction with implicit lighting and material. In this work, we address the challenging problem of multi-view 3D surface reconstruction. Given 2D images capturing a real object from multiple views, our goal is to infer the 3D geometry of the object, its appearance, and the cameras which capture those images. We present implicit differentiable renderer, a neural network architecture that simultaneously learns those 3 unknowns. IDR able to produce high-fidelity 3D surface reconstruction by disentangling geometry and appearance, learned solely from masked 2D images and rough camera estimates. A recent successful neural network approach to solving this problem is by feeding those 3 unknowns into a differentiable rendering system. That is, simulate the rendering of the scene from a given view and comparing the rendered image to the original image. The key challenge is how to make the renderer a function of the geometry that is independent of the object material or the scene lighting. A recent work by Naimer et al. Introduced such a differential rendering model that can represent arbitrary texture but cannot handle reflectance and lighting effects, nor can it handle noisy cameras. Concurrently to our work, NERF used neural rendering for novel view synthesis from a set of images with known cameras, where differently from IDR, the method doesn't produce a surface reconstruction of the scene geometry rather than a 3-dimensional density field. In our work, we reconstruct an implicit surface together with surface light field that is separated from the geometry, and we can handle both exact and noisy camera information. Our geometry is represented as the zero-level set of a neural network F, which model for each 3D point its sign-distance function to the shape. Given a learnable camera position and some fixed image pixel, we would like to produce differentiable RGB values. The camera orientation and pixel define a viewing direction, and we can trace for the first intersection of the viewing ray with the implicit surface. The first step is to represent the intersection point and its normal as the differential functions of the implicit geometry and the camera parameters. We implement it by simply composing the neural network with a fixed linear computation at its entrance and another at its output. Secondly, we want to approximate the color of the pixel, determined by the radiance reflected from the surface to the camera. Our interest is that the renderer will not memorize any part of the geometry or the viewing cameras. Therefore, we suggest representing the light field as a function of the surface position, surface normal, and viewing direction. This is implemented using a second neural network to output RGB values. Incorporating the normal and the viewing direction is necessary for 3D reconstruction that is decoupled from the appearance and the cameras. This claim can be explained using this simple example. A renderer without normal will produce the same light estimation in those two cases, therefore can result in a renderer that compensates over geometry properties. A renderer without viewing direction will produce the same light estimation in those two cases, where in real life the scene appearance is likely to be view-dependent. To complete the IDR model, we introduced a global feature vector of the geometry to get our final radiance approximation, which then compared to the ground truth pixel color to simultaneously train the model's parameters. We apply our multi-view surface reconstruction model to real 2D images from the DTU dataset. Here, we show the reconstructed geometry, i.e. the zero-level set of the implicit function f, and rendering of novel views gained from the neural renderer M when using fixed ground truth cameras. Towards the goal of disentangling geometry and appearance, we show that we're able to transfer the appearance learned from one scene to different geometry by simply switch between the rendering networks. Note that without using the normal in the renderer, the geometry is not well approximated, and the renderer fails to produce a plausible rendering of different geometries, although the light field approximation looks reasonable. Here are results in the setup of trainable cameras with noisy initializations. We show our surface reconstruction compared to the popular non-deep learning approach CoLMAP. We further show results of IDR training with fixed cameras set to the inaccurate camera initializations. This indicates that the optimization of camera parameters together with the 3D reconstruction is indeed significant. Here are some more results of our method. For more details, you're welcome to take a look at our paper. And stay tuned because our code and data will be available soon. Thank you for listening.
We present neural radiance fields, or NERF, a new method for representing complex scenes that achieves state-of-the-art results for view synthesis. Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation of the scene as a vector-valued function, which is defined for any continuous 5D coordinate, consisting of a location and view direction. We parameterize this scene representation as a fully connected deep network that takes each single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We can then use techniques from volume rendering to composite these values along a camera array to render any pixel. This rendering is fully differentiable, so we are able to optimize the scene representation by minimizing the error of rendering all camera arrays from a collection of standard RGB images. We first show comparisons to top-performing methods on synthetically rendered data. Scene representation networks implicitly represent a scene using a fully connected neural network. SRNs have issues with multi-view consistency and are unable to represent high-frequency details. Local light field fusion uses a pre-trained network to promote each input view to a high-resolution 3D volume. Inconsistencies between adjacent volumes causes flickering artifacts. Neural volumes encode a scene as a 128 cubed voxel grid and use a warp field to better allocate these limited samples. However, they're still unable to represent high-resolution content, such as the fine details in the ship's texture and rigging. We see the same trend in all of our synthetic test scenes. Our method both qualitatively and quantitatively outperforms the other methods. Here we show the results of our method on the 6 other objects in our realistically rendered dataset with complex geometry and non-Lambertian materials. Next, we will show comparisons on real scenes captured with a forward-facing phone camera. SRN uses a recurrent network to ray march through encoded scenes, resulting in inconsistent appearance between rendered views. LLFF blends between multiple renderings with different limited fields of view, resulting in flickering artifacts along image borders. Here, only our method can represent fine details with complex occlusion effects, such as the ribs in this fossilized T-Rex skeleton. Now let's take a look at some additional real results. We can visualize the view-dependent effects captured by our representation, such as the semi-transparent appearance of the olive oil bottle and specularies on the stove, reflections on this room's television and specularies on the conference table, and sharp reflections and specularies on this red car's body and windshield. Our representation captures high-quality scene geometry, such as the details on this red flower, and complex occlusions in the Christmas tree leaves and ornaments. This geometry is precise enough to be used for additional graphics applications, such as virtual object insertion with convincing occlusion effects. Here, we visualize additional results across a wide variety of real-world scenes, each captured with only 20 to 50 input images. Our neural radiance field representations are able to render photorealistic novel views of entire scenes with fine geometry details and realistic view-dependent reflectance effects. We're able to capture all of this visual complexity in just the weights of a simple, fully connected network. We also show preliminary results for 360-degree capture of real scenes.
We present Pix2Surf, a method that learns to generate a continuous parametric surface model of objects from one or more images. Given a single view of an object, our goal is to reconstruct a continuous 3D surface for the visible parts of the object. Given multiple views of an object, we aim to reconstruct a continuous 3D surface that is consistent across views. Even with multiple images, this is a challenging problem when camera baselines are large or lighting and occlusions are inconsistent across the views. An ideal multi-view surface reconstruction method should have the following properties. First, we want to generate continuous 3D surfaces that can be arbitrarily sampled to generate high-quality geometric models. Second, we want the generated models to be geometrically consistent across views. And finally, we want the input pixels to be in accurate correspondence to the generated shape. We build upon 2 previous works for 3D shape reconstruction. The approach by Sridhar et al. Uses the Knox map representation to reconstruct a point cloud. This shape is consistent across views and is in correspondence with the input pixels. However, the reconstruction is a discrete point cloud. AtlasNet, on the other hand, reconstructs a continuous shape but lacks consistency across views and pixel correspondence. Pix2Surf is capable of reconstructing a continuous and consistent 3D surface for an object seen from one or more images. Note that our method retains 2D pixel to 3D shape correspondence, thereby allowing us to lift texture directly from the input image. We first describe the single view, single chart version of Pix2Surf. Given a single input image, we use an encoder to extract image features. The Knox UV branch then predicts the Knox map and mask for the object. Note that the Knox map here is not our final 3D output, but acts as an intermediate supervision signal for the network. In addition, we also predict a 2-channel output where we see the emergence of a learned UV map or chart. The visualization on the top right is in image space. The unwrapped chart refers to a visualization of pixels using the predicted 2-channel learned coordinate. Here we show the unwrapped learned chart. Note that the points on the learned chart are in exact correspondence to the input pixels. We use a code extractor to obtain an image-level latent code. The learned UV chart coordinates are passed through an amplifier network to extract the amplified UV coordinates. The surface parameterization branch learns to predict a continuous surface from the passed latent code and amplified coordinate. The 3D surface generated by our approach is continuous, and 2D image pixels are in exact correspondence with the 3D surface. This allows us to transport texture information directly from the image. Here we show some results from our single view, single chart approach. When multiple views are available, we can naively combine the individual charts. However, this naive combination leads to shape discontinuities. To overcome this limitation, we developed a multi-view atlas version of Pix2Surf. For each input view, we extract latent codes that summarize the shape as seen from that view. This multi-view method has 2 key features. First, we max pool the latent codes from each view to promote feature-level multi-view aggregation. The max pool feature is concatenated to the amplified UV coordinates. We predict 1 chart per view and thus have an atlas over multiple views. A shared surface parameterization branch then predicts the continuous 3D surface for each view independently. During training, an additional consistency loss enforces corresponding points to lie in similar 3D locations on the surface. Here we show some results from our multi-view atlas approach. Our method features 2 remarkable emergent properties. First, the learned UV chart is fully unsupervised, yet learns a consistent unwrapping of a 3D shape onto a chart. We observe this result in both the single view and multi-view methods. Second, for the multi-view method, the learned UV chart shows that corresponding points across 2 views are mapped to similar locations on their respective learned charts. Thus, our method discovers the notion of cross-view correspondence without explicit supervision. Please see the paper for more details. Thank you for your attention.
Hi, my name is Vincent and I'll talk about scene representation networks, a continuous 3D structure-aware neural scene representation. Scene representation networks allow you to go from a single observation of a simple scene, such as this image of a ShapeNet car, to a full 3D reconstruction of the underlying scene, enabling perfectly multi-view consistent null view synthesis and giving you a full shape reconstruction. To this end, scene representation networks consist of 2 main parts. The first one is the neural scene representation itself, which represents the underlying 3D scene, and the second is a neural renderer that renders this neural scene representation from arbitrary camera perspectives. Let's first talk about the neural scene representation. Scene representation networks encode a scene in the weights of a fully connected neural network. That fully connected neural network maps an XYZ world coordinate to a feature representation of whatever is at that XYZ world coordinate. Consider the simple toy scene on the left-hand side. Gray is free space, and then there's 3 objects, a circle, a square, and a triangle. All the X coordinates within the blue triangle should be mapped to a feature that says I'm a triangle and I'm blue. All the X coordinates in the red square should be mapped to something I'm a square and I'm red. And all the X coordinates in free space should be mapped to something that says I'm free space. This implicit representation has a number of advantages. First, it strictly enforces 3D structure, because the input is just a 3D coordinate. It can be sampled anywhere, and it can be sampled at arbitrary resolutions, because it's just a continuous function defined on all of R3. It parameterizes scenes smoothly, without any discretization compared to voxel grids, or point clouds. And the memory this requires scales with the complexity of the underlying scene, and not with some sampling resolution. Okay, that's our neural scene representation. How does the renderer work? Let's consider a little toy scene again, and now we place a camera, and we want to render our scene from that camera perspective. First, we'll have to find the intersection of each camera ray with scene geometry. And for that, we'll do ray marching. Let's take a look at the single ray here. We'll start close to the camera at the coordinate x0, and we'll sample our scene representation network at that world coordinate. And that gives us a feature vector that describes the local properties of that coordinate. Now, we'll use a fully connected neural network to translate that feature vector into a step length, and we'll advance along the ray according to that predicted step length. And this is similar to the so-called sphere tracing algorithm proposed in the 80s for marching signed distance functions. Now we'll iterate this algorithm for a fixed number of iterations, and we call the last iterate our estimate of the intersection of all of the rays with scene geometry. Now we need to render a color for each of the rays, and for that we'll sample our scene representation network at final time and translate the resulting feature vector into a color using another fully connected neural network. Now we have our neural scene representation and our neural renderer together, and we can train this thing end to end on a data set of only 2D images and their camera pose and camera intrinsic parameters. Scene representation networks was the first implicit representation that allowed you to train it only with 2D observations. Let's talk about a few related 3D scene representations. First, there's PyFu, proposed by Saito et al. In 2019, which generalizes across scenes for single-shot reconstruction, but requires ground truth shape information at training time. Next, there's voxel-based representations, such as deep voxels on low volumes, which do not require ground truth shape information, but do not generalize across scenes either, requiring overfitting on a large number of observations of a single scene. The same is true for the recently proposed NERF, which requires overfitting on a large number of observations of a single scene and does not generalize. Let's take a look at a few results of scene representation networks. First, we're considering single-shot reconstruction of ShapeNet objects. We train on the ShapeNet training set and then reconstruct an object from a single observation at test time. You can see the input observation on the lower left-hand corner. In the top row, you can see the output of scene representation networks, and you can see that it's the only architecture that enables perfectly multi-view consistent null view synthesis. Furthermore, scene representation networks also give you a reconstruction of shape, because you know the length of each ray that you cast. Here we visualize this with normal maps. Scene representation networks allow you to render at any resolution. This model here was trained at a resolution of 128 squared, but at test time you can simply shoot rays more densely and render the object at a resolution of 512 squared. Scene representation networks allow you to generalize to completely unseen camera perspectives. This model has never seen a car up close or a car on its head, yet extrapolates to these camera perspectives perfectly. Trying the same thing with a convolutional neural network fails completely, as the training set does not have any support for these camera perspectives. Finally, scene representation networks also allow novel view synthesis in room scale scenes. Here's an example on the simple scenes from the DeepMind generative query network paper. However, for now, we're constrained to these simple scenes. Thank you for your attention.
We present texture fields, learning texture representations in function space. In recent years, learning-based methods have shown remarkable results on 3D reconstruction of shapes. However, 3D objects do not only consist of geometry. Much less attention was spent on reconstructing the appearance of objects, even though texture, for example, is a characteristic property of an object. We propose a novel method that can reconstruct texture from a single image and a corresponding 3D shape, and a generative model for novel textures. One of the major limitations of current methods result from the representation of the texture. Using colored voxels as representation, deep learning architectures are feasible on the 3D grid. However, due to high memory costs, methods are limited to low-resolution discretization and hence also to low-frequency texture. In contrast, texture atlases can represent high-frequency texture. However, they rely on a UV mapping that is restricted to predefined template models. Moreover, texture atlases are prone to discontinuities of texture information. To solve these limiting factors, we propose a novel texture representation. Our representation is independent of shape discretization. Therefore, it allows for representing texture at arbitrary resolution. Furthermore, this method does not require template models, and it's independent of shape representations, so it can be applied to any 3D model. Inspired by recently published continuous representations of 3D shapes, our novel texture representation is based on regressing color values in the 3D space. We represent texture by learning a continuous field parameterized with a neural network. This network maps any 3D location to a color value in the RGB space. By evaluating the texture field at any location on a shape, we can extract texture, for example, on the shape, or for image pixels using corresponding depth and camera information. For reconstructing texture, we condition the texture field on a global shape embedding, as well as a global feature embedding of a condition, for example, a single image. The texture field learns to predict the color value following the provided conditions. Furthermore, we used our novel representation for a generative model. Our setup consists of a variational autoencoder with the texture field as the decoder. At inference, we can sample novel textures for a given 3D object. We applied the conditional model for single-view texture reconstruction. The model is trained in a supervised fashion on single categories of the ShapeNet dataset. Our method is able to reconstruct plausible textures from a single image for the corresponding shape. We compared our method to a novel view synthesis baseline that uses a simple UNet architecture. In contrast to the baseline, our model inherently fulfills 3D consistency. While trained on synthetic input images, our method generalizes reasonably well to real input images. We combine texture fields with the shape reconstruction method occupancy networks and build a full pipeline for 3D reconstruction of shape and texture. Our generative model is also trained on ShapeNet data. Here are some interpolations in the latent space. For all three models, the texture is generated from the same latent code. Our generative setup can also be used for transferring texture from one model to another. Thanks for watching our video.
Hello everyone, I'm very happy to share my work on surface-based representation of 3D shapes. This is joint work between ENPC with Théo Deprel and Mathieu Aubry and Adobe Research with Brian Russell, Matthew Fisher and Voveke. There are several ways to represent 3D shapes, which is the motivation for this workshop. In this talk, I discuss a 3D representation based on surfaces. A surface representation can be used without post-processing to do rendering, to compute surface interactions, to penalize surface interpenetration, and as we'll see in the talk, to compute shape correspondences. Our key idea is a new parameterization of 3D surfaces based on deformations. We parameterize a target 3D surface by the deformation from a template surface to the target surface. Of course, this requires a template, and we're going to discuss several cases. The first case, which is the simplest one, is shape categories with a clear shape template, such as human body scans. We'll discuss later harder categories which do not have a clear template. Let's see now how we can parameterize these surfaces in practice. We propose to model the surface deformation by a multi-layered perceptron, an MLP. This MLP is supposed to deform a common template into a target surface, so it should be conditioned to do that on the target shape and the template. More precisely, we condition the MLP on the target shape embedding, obtained by a shape encoder such as PointNet, and a 3D surface point on the template, such that the MLP, given the target shape embedding, acts as an R3 to R3 function, taking a point on the template and outputting a 3D point on the reconstructed shape. This R3 to R3 function is run in parallel on all the template points, which results in a reconstructed shape with the same number of points as the template. Since the MLP deforms each template points independently, this means that there is a 1-1 correspondence between template points and its deformed version. We say that the reconstruction is thus in dense correspondence with the template, and visualize this with colors. An important aspect of the method is that the MLP is conditioned on the embedding so that each transformation is specific to the current sample. In fact, the key novelty here is to use MLPs as a family of parametric and continuous functions, and just use the embedding to predict which specific instance in that family we want to use for the current sample. These MLPs are trained on a large shape collection, and there are two cases. Either we have correspondence annotation in the dataset, and we can use these MLPs with a fully supervised L2 loss, or we don't, and we use an unsupervised reconstruction loss, like the chamfer's distance, and we couple it with regularization losses that penalize distortion of the surface. Since our method has a fully unsupervised setting, regardless of how we train the MLP on the collection, we can always refine the learned deformation by a test time optimization on a new test sample using our unsupervised losses. The variable that we optimize here is the embedding of the test sample, and we initialize the optimization by the learned embedding. After optimizing the embedding, the quality of the reconstruction have improved. If the initial reconstruction is good enough, this test time doesn't change much. However, it is critical if the initial reconstruction has clear artifacts, as you can see here on the arms. This reconstruction approach by surface deformation is robust to noise, holes, partial scan, and generalized to difficult poses and shapes. It is time to wrap up. We have seen how to parameterize the surface of 3D shapes with neural networks by their deformation from a template surface. And we have shown the strengths of this approach in several applications doing analysis by synthesis. In particular, we showed that surface deformations could be used for shape matching to learn parts, and just recently to do clustering, which is work on archive. Check it out. Thanks a lot.
Hi everyone, my name is Jung-Jin Park, and I'm going to present DeepSCF, which was introduced in CVPR 2019. And this work was done with Pete, Julian, Richard, and Steve. Deconvolutional neural networks have been the key components driving the progress into the computer vision. And the convolutional layer operates on a discretized 2D grid pixels. But the direct extension of convolution to 3D does not scale well in space and time when directly applied to voxels. More compact representations such as point clouds do not describe surface, and triangle meshes come with unknown number of vertices and topologies. Instead, we take a fundamentally different approach, which is to describe 3D surface as a decision boundary of a neural network. The key idea is to directly regress a continuous SDF with a fully connected neural network. Specifically, this neural network takes XYZ position as input and outputs SDF for that point. Sign distance function is a volumetric field where the magnitude of a point represents the distance to the closest surface, and the sign indicates whether the point is inside or outside of the shape. Thus, the surface is implicitly represented as zero level set, where the SDF value is equal to 0. Sign distance field is a widely used concept in 3D computer vision, but most of them use discretized voxel grid of stored SDF values. Such discretization significantly limits the expressive power of the deep learning methods in 3D. Instead, we can directly regress the continuous SCF with a neural network by training it on the point samples of a shape's SCF. The resulting network can express the fully continuous SCF, meaning that we can query an arbitrary continuous point location and get the SCF for that point. The universal approximation theorem states that a fully connected network can describe an arbitrarily complex decision boundary. Thus, we should be able to represent an arbitrarily complex 3D surface given enough weights. The implicit surface of signed distance field can be converted into a mesh by conducting Marching Cubes algorithm. Alternatively, we can shoot rays along the camera ray direction until it meets the zero crossing to render a depth map from a particular viewpoint. Note that this ray casting is fully differentiable because the neural networks are differentiable. Another nice property of DeepSCF representation is that the surface normal can be analytically computed by taking the gradient of the SCF with respect to the XYZ coordinate of the surface points. So far, we explained how a single shape is modeled. We can extend DeepSCF to model a dataset of shapes by conditioning the network using latent code Z. This latent code encodes the information of a shape that can be interpreted by the decoder network. Now the question is how to obtain the meaningful latent space of shapes. Traditionally, this was done by training an autoencoder. However, it is not clear for us how to design an encoder to process a continuous signed distance function. To avoid designing an encoder, we introduce a learning scheme that we call autodecoder, where the code is directly optimized through backpropagation. In the beginning of the training, we randomly initialize a code per object in the dataset. We then jointly optimize all the latent vectors in the dataset, along with the weights of the shared decoder network using the standard backpropagation. The objective function is to minimize the L1 loss between the predicted and the ground truth SCF. Now, after the training, we have a meaningful latent space of shapes, and we can verify this by showing the interpolation in the latent space. This video shows the latent space interpolation between a pair of training codes. The visualization shows that the new representation produces high-quality continuous surfaces with complex topologies. We note that the size of the network trained on thousands of shapes is only about 7 MB, which is half the size of a single shape's uncompressed voxel grid. During inference, we find an optimal code that best explains the input shape using gradient descent. Note that during the optimization, the trained decoder weights are kept frozen and only the code is optimized. Inference can be done for reconstructing a full 3D shape, but our autodecoder formulation allows inference on arbitrary number of SCF samples. For example, finding optimal code from a single depth map. A powerful property of autodecoder inference is that we can add priors in the optimization. For example, we can add a distribution prior to the optimization, or we can ensure that the resulting signed distance field or surface normal are geometrically correct. Here we show a visualization of the inference process. The optimization tries to find the best code that matches the single depth map observation, shown as green dots in the middle. Compared to an octree-based method, DeepSCF generates higher quality shapes with surface normals while having 100 times smaller network size. Compared to a mesh-based method, DeepSCF provides more detailed reconstruction. Thank you for listening.
Hello, everyone. Welcome back to the 3DReps workshop. While we wait for people to trickle in, maybe we should ask our next invited speaker, Tom Funkhauser, to test his screen sharing and audio.
I can't start my video because the host has stopped it.
Oh, I see. Let me see if I can fix that. Okay. Yeah, good. We can see your screen, Tom.
Great.
Great. All right, so people are still trickling in, so let's give it a minute. And meanwhile, so I had a peek at the gather.town session, and it seemed like there was very active participation. At some point, I saw more than 40 participants. So I'll pass the stage along to Or, who's going to tell us a little bit more about what he saw in Gather and introduce our next speaker.
Yeah, in the meanwhile, Srinath, if you could maybe post a message on Gather, because I know some people on Gather closed their Zoom window to not interrupt their audio. So maybe post a message there that we're back.
Okay, I posted already,
Thanks.
but I will do that again. Thanks.
Oh, okay, great. All right, so let's wait a few more minutes. Yes, since this was a slightly less conventional experiment, we'd love to get any feedback from you afterwards via email or in this chat. I found some useful conversations with presenters in the poster session. I hope you did as well. And there's a suggestion here that we can actually go around and gather people to join this room, old school style. So that's if you want to go ahead and do that, grab people. I don't think there's a grabbing functionality in Gather.
Can you confirm that you can see?
Sorry?
I was just going to say, can you confirm you can see my slides at this point?
We can, and now it's full screen, so it's even better than previous.
All right, excellent.
So let's wait like 30 seconds, and I'll introduce you, and we can get started.
Sure, perfect.
Okay, so let me welcome everyone back in. I hope you enjoyed the poster session. Our next speaker, I'm honored to present Professor Tom Funkhauser. He will be talking about learning implicit 3D shape representations. So a little bit about Tom. Thomas Funkhauser is a senior research scientist at Google and the David M. Siegel Professor of Computer Science Emeritus at Princeton University. He receives his PhD in computer science from UC Berkeley in '93 and was a member of the technical staff at Bell Labs until '97 before joining the faculty at Princeton. For most of his career, he focused on research problems in computer graphics, including foundational work on 3D shape retrieval analysis and modeling. His most recent research has focused on 3D scene understanding in computer vision. He has published more than 100 research papers and received several awards, including the ACM SIGGRAPH Computer Graphics Achievement Award, ACM SIGGRAPH Academy, ACM Fellow, NSF Career Award, Emerson Electric. This can go on forever, literally, tons of awards. And also a Google Faculty Research Award, University Council Excellence in Teaching Awards, and a Sloan Fellowship. So Tom, we're all very much looking forward to your presentation on this hot topic. So the stage is yours.
Thank you very much.
I just remind you that in 20-minute time, I'll remind you that there are 5 minutes left, and I'll remind our attendees that use the Q&A to ask Tom questions, and I will read them to him at the end of the presentation.
Okay, perfect. Thank you. Okay, so yeah, I'm going to talk about 3D shape representations. Not a big surprise. I'm going to try to motivate this by applications where you need to know the shape so that you can interact with it. So in a robotics application, for example, you might have a grasping arm that wants to know the shape so that it can model grasps, as an example. For many applications like this, there's a set of properties that you would care about in a 3D shape representation. One is that it can accurately represent shapes, not approximately like coarse voxels, but quite accurately. That it's general, it works for any kind of object or scene. That it's concise, the amount of data it uses isn't too much, that it's structured, that it maybe has information about how shapes decompose into different regions or how shape collections are related to each other, those kinds of structures. That the kinds of operations that you might care about, like querying inside, outside, or distance to the surface, or things like that, are supported efficiently. That it can be learned from a shape prior, and that it can be inferred from images, in particular maybe depth images for a robotic application. Okay, that's all motherhood and apple pie, but very few representations actually have that. So if we look at traditional representations that are explicit, like meshes or voxels or things like that, they're often very accurate and general. So we can have meshes that describe cars and airplanes and molecules and lots of different shapes. And with an infinite number of triangles or voxels, points, you can represent anything. But they're generally not very concise if you get that accuracy. They have no structure. Inside, outside are difficult to query for a mesh, say. Marching along the surface is not so easy for voxels, so on and so forth. And they have no prior at all, and they're difficult to infer directly. So as everybody knows, 5 years ago, people started looking at learned representations where you might have an autoencoder that takes in some sort of observation and makes a latent code out of it. And then there's a decoder. And those methods can produce very concise representations of shape if you ignore the number of parameters in the decoder, which are shared among all objects, so they're not per object. Then the latent codes are very small. They obviously encode shape priors, and they can be inferred from a variety of things. They're not so structured. There is some structure in the latent codes where this is a picture of, say, a T-SNEEZ plot where things are colored by semantic class. And so, yes, there is some structure to the latent codes, but it's not like it's structure that you can use for collision detection or any kind of other like decomposition into parts or things like that directly. And then they're often not queryable or very accurate, or certainly not general. Most methods are trained on a small number of classes, and then they don't generalize to things at all that aren't in those classes. Okay, so then, as everybody knows, recently in the last year or two, there's been a lot of work on implicit 3D shape representations, where we take in an observation into an encoder and we make a latent code the same as before, but instead of just decoding that to an explicit representation, instead the decoder operates as a function where you might take in X, Y, Z and then output a function like sign distance or occupancy or something like that. Great, you all know that. And we can then, given such a function, reconstruct explicit representations of the shapes, say by sampling lots of places and running marching cubes. Okay, so these methods are much more accurate than the previous learned methods, but they aren't very general. Again, they're usually demonstrated for a small set of classes, and if you if you gave them a test example that's really far away from anything they've seen before, they would be very bad. And they have some structure, and they're more queryable, especially if the query you want to do is exactly the query that the decoder can do. But they still don't really have quite the structure and accuracy that we would like. And then there's, of course, many advances that have been made very recently, including these are just a list of papers that are being presented at this workshop in the last hour. And each of them improves some of these properties in some way, but there still isn't really a representation that provides both structure and accuracy and generalizes to a wide variety of objects. So I'm going to talk about two papers in this work that are aimed at that set of properties, including decomposing objects into their structure and being able to represent them accurately and then to generalize better to new shapes. Okay. So the first paper I'm going to talk about is this one called Structured Implicit Functions that was presented at ECCV in 2019. And it was done, as was the second, by Kyle Genova, who is a PhD student at Princeton, who's been an intern at Google for the last while. Okay, and this is a paper that was jointly done between Princeton and Google. Okay, so in this work, we're going to use a network only to infer the structure of a 3D shape. It's not gonna use a learned implicit function like an occupancy net. In the second part, we'll start doing that. But in this part, we're just gonna use a network to infer the structure. And the goal of this part is, given an input, which could be an image or a depth image or a 3D shape or something like that, run it through a network and output a structured decomposition of the shape, where in this case, the structure is going to be a mixture of Gaussians. So why a mixture of Gaussians? So a mixture of Gaussians is you have a set of Gaussians that are located in space, and let's say you have 100 of them, and any given value x, a position x, you evaluate all the Gaussians and you sum up the values of those Gaussian functions, and that gives you a value for the function, the implicit function. And then of course, like other implicit functions, there's going to be a level set value that's on the surface, and greater than that's outside and less that's inside. In computer graphics, these things would be called blobby models or metaballs or soft objects. They go back pretty far well into the early 80s as a representation of 3D shape. Why do I think they're good as a way for deep learning? Because they're small, they're smooth, continuous, and the derivatives of moving the parameters of the Gaussians changes the shape in a continuous way that I think makes learning easier. They also can represent complex shapes approximately by having not too much data. So this, what I've been showing you on the right, is from 1991, representations where people use more and more Gaussians to represent more and more details and shapes. So what we're going to do in this work is we're going to use the reconstruction you get from a mixture of Gaussians as and then compare that to a supervised ground truth surface, and then we're going to learn a network that can produce those parameters for any input. The actual parameterization of our Gaussians is there's a center for each Gaussian, there's a rotation to it, there's a radius, 3 radii, so on and so forth. There's also the CI parameter, which is on the left, which is a magnitude to that Gaussian. And that's kind of important because we end up using a fixed number of Gaussians to represent all objects, say 100. And the CI parameter can go to 0. So the network can learn to set it to 0, which is basically turning off one of the Gaussians. And so for different classes where you have extra and missing parts, it can learn to turn on and off different Gaussians, which is quite important. So the way that we actually train this is that given some sort of input, let's say it's a 3D surface, a training time, for example, we decoded it into a stack of depth images, 20 depth images just as a way to give it into the convolutional network. And then the network directly outputs the parameters of the Gaussian. So the colored vertical line here on the right is representing the Gaussians for this shape. Each of those is 10 parameters, 3 for rotation, 3 for position, so on and so forth. And there's some fixed number of these Gaussians that are output directly by the network. And then the reconstruction is performed from those Gaussians and then compared to the input to see whether it was to compute the loss. The reason that this might be good is because it provides a supervision for a decomposition of shape into regions, so into structure, such that we can use a reconstruction loss as a meaningful signal for are we decomposing well. So we are quite bottlenecked on the number of Gaussians we can use, so they have to be used efficiently, and we have to reconstruct the surface to do well on our loss, and so that forces the network into learning useful structures. It also is the case that there's a lot of consistency between the distribution of the Gaussians that you get. I'm going to call them Gaussian blobs across different examples within the same class or even across classes. If you were to look, say, the tip of the wing, there's like a teal colored Gaussian that's shared among all these different airplanes, even though the shapes of these airplanes are very, very different. And so, and if we were to interpolate between these, those would move smoothly between them. And so it provides again, a kind of a continuous representation for variations of shape, region-wise. And then they can represent their implicit functions, so they can represent varying topology smoothly. And then they also represent a fairly expressive shape space. So this video, which I'm going to show if it plays, is going to show on the left, this is a laid out shape space where the 10 dimensions times however many blobs you have. So in this case, there's I think 100 of the Gaussians. So it's a 700 dimensional space laid out on the left as a t-SNE. In the middle is the set of Gaussians for each of the shapes, and on the right is the reconstruction. And this red dot that is kind of going through the shape space is showing you basically an interpolation, a navigation of the shape space, and how the blobs move as we navigate through that space, and what the reconstructions look like. And when you transition, this is trained on multi-class, on all 13 classes of the R2N2 data set from ShapeNet. And when you're moving within a class, the blobs move extremely continuously, and there's a great correspondence, even semantically, between the different parts. So here's different airplanes, and you can see that they move continuously. When you move between classes, there's less of that. It has to figure out how to use exactly the same set of blobs to represent a completely different shape. But within category, there's an incredible consistency for different shapes within the space. So the short version of that part of the talk is that it's possible to take a network and learn decomposition of the shape into local regions. And those local regions, the fact that they're represented by an implicit function as a mixture of Gaussians is, I think, what makes it able to learn kind of complicated decompositions and complicated shapes across multiple classes. Okay. So that's not the whole story, though, because we would like to do better than that. The reconstructions we get from that are pretty poor. I mean, all we can do is reconstruct a mixture of Gaussians. Yes, that's an implicit function, but it's not learned. So we're going to augment that representation by storing a local latent vector for each of the Gaussians. So these little rectangles on the right are representing little latent codes. And we're going to use an occupancy network style network to decode a function from each of those latent codes, and then use those along with the Gaussians to recover our overall 3D function, which is going to give us much better reconstructions. So that's basically the shape representation that I'm going to advocate for in this talk. The way that we actually train on that is that, say, if we had depth images or something like that as input, we would run it through the network that I described in the first part of the talk to produce the mixture of Gaussians, the decomposition into Gaussian regions. And then we would also train a local shape encoder to learn the local codes for each of these Gaussians. And the way we do that is that we would extract point samples from the input, give them through the, create a local frame based on the parameters that were extracted by the structure decomposition, and then learn with a point net a local code for each of those local regions. Although this is going to flip by in the talk, that this is a significant part of the reason that we are able to get good reconstructions, is that we don't have one global encoder for the entire shape. We have local encoders for local regions, and so they are able to better produce. Their shape spaces are simpler because they're they're small local regions, and then of course they're also generalizable because they're small local regions, and so then our final representation is like I showed, where there's these template parameters, which are the Gaussians, and then each of the Gaussians has a latent code with deep features. So then we have a decoder that will decode the deep features with an occupancy network kind of network to produce a function. And then we also use the Gaussian values from the first part so that we can control the local extent of each of these functions and multiply them together to get back a local function that gets summed to produce the overall local deep implicit function. So the final function then is this composition of all these local functions that are learned. So the results that we get from doing that are being compared here to things that appeared before this summer, before CVPR 2020. The SIF here is what I described in the first part of the talk, structural implicit functions. The RS is the deep local implicit functions that I just described. Occupancy network is a good baseline to compare to, and this shows one example. Here's another example. This is an autoencoding where the input is a three-dimensional point cloud and the output is these local function, these implicit functions. Here's another example. Ours is just better able to get the local details of many of these shapes. If we look at the F scores on the R2N2 13 class trained multi-class, and compare it again to occupancy network, the left shows the types of numbers that you normally see. The right shows a ranking of the shapes in the data set according to the F score that our method produces. Easiest is on the left, hardest is on the right. And then the curves are what is the F score of each of the methods for that ranking of shape. And so the very right is our worst example. That's actually shown as an example on the far right. And our very best is in the left part. And I think this is actually a meaningful curve. I think that these mean numbers that you see in tables on the left are misleading. And so you have to actually look at the whole curve in order to really understand which shape methods are better than others. We also did experiments where we try to generalize to other classes. So this example shows a piano, a printer, and a camera, which are quite different than the categories that we would get from the 13 class data set in R2N2, 3D R2N2. And the F scores you get are quite different from previous methods, 84.4 versus 66.6 on average. And then if we do depth image completion as an application of this, again, we get quite a significant increase, something like 16 points or 15.5 points of F score compared to the previous state of the art at that time. So that's better accuracy than previous methods, but it's also faster. The decoder for LDIF only needs to decode a local region of space, not an entire shape. And even better, it only needs to decode the differences between that local region of space and the Gaussian function. And since the Gaussian function already captures a lot of the global shape for that part, then the shape that it has to decode is actually much simpler. And so we are able to get by with decoder networks that have less than 1% of the decoder parameters of other networks like an OCNet or something like that. And although we have to evaluate multiple local networks for each point, the Gaussians don't overlap very much. And so then it's not like if there's 100 Gaussians, we have to evaluate all 100 of them. Usually it's like maybe 3 or something like that for any given point that actually are being influenced. So anyway, so the main takeaway here is that this shape representation has many or basically all of these properties. It's more accurate. It's not perfectly accurate. It's generalizable because it's representing local shapes. It's learning local shapes, not global shapes. It's concise, and it decomposes into the structure, and in fact, into a structure that's consistent across a class, and so on and so forth. So I described two things in this talk. One is the decomposition into local implicit functions, and then the other was the learning latent codes for them. They've only been tested in ShapeNet's kind of settings, not for scenes or not for crazy other kinds of shapes, and so we don't really know how far that they'll extend. I think they are the right way to think about how to make a representation. How to infer them is going to depend on the type of data that you have. This particular method also requires an inside-outside in the way that we trained it, whereas maybe we could train it with a site-agnostic loss or something like that instead. We didn't do that. If you think about what's in extensions and variants are useful, there's lots of them, and people in this workshop are already doing them. So this is a little bit late, but so we advocated for local regions. In another CVPR paper, we had latent codes on grid cells, and so that we could more accurately encode and decode local shapes and so on and so forth. And so that's a similar idea, but just with a different decomposition. And so what other decompositions make sense that are easy to infer and consistent and the different properties you want. In this we only looked at giving it an XYZ and then reconstructing the shape. But of course, other people have looked at giving it also a direction and then predicting some function of a 5D instead of 3D. And so then can these local implicit functions and be useful for that as well? Is an interesting question. What function output should we be producing? So far people have mostly looked at sign distances and inside outside and colors, radiance values and things like that. Maybe even BRDFs. But I think that the real thing here is can you use these representations in applications? And so if you thought of yourself as a robotics application, you might care about, if I push it with this force in that direction, how will it accelerate? Or things like that. And so I think that we should broaden how we think of the functions that we're trying to predict with these implicit functions. And then of course, how do you learn the right decoder weights? Do you overfit to a test time? What's a free variable and what's not for each given example is a very interesting thing. And I'm sure you're all aware of NERF, but that's very inspiring with regards to not just optimizing latent codes, but actually optimizing latent network weights for each example. Anyway, so I will stop there by thanking my co-authors on these papers, in particular Kyle Genova, who's a superstar. And take any questions or stop from there.
Thank you so much, Tom. This has been great and definitely very exciting and very relevant and summarizes lots of interesting works. We have a bunch of questions for you, both some I got in private messages, some are in the Q&A. I'll read them to you. So one question from, a room number. So let's say anonymous. Question on local deep implicit function. All methods seem to struggle in fine detail. Why is that? And have you tried to resolve this somehow?
Well, that's the point of the second half of the talk, is that the methods struggle in local details for two reasons. One is that the encoder, if it's a global encoder, does not get a chance to focus on the local details. It spends most of its effort on the global details, or frankly, maybe even just recognizing the shape. I'm sure you're all aware of the hypothesis from Vladlen's group that most of the encoders are just recognizing the shape, and a nearest neighbor query would have been just as good. So you need to get past that. If you're getting 57 or 58 IOU on your shape reconstruction from RGB, then you're probably just recognizing the shape, not actually encoding it. And so the point of this was to locally encode regions in a way that it couldn't just recognize and then decode similarly. And so by doing that, we can get higher details. Details in this method are not perfect, but I think that is the right way to go. Did that answer the question?
I think so, yes. We have another question from Brent Griffin. Thank you for the great talk. What happens if you increase the number of underlying Gaussians for these representations? I would think detail accuracy would improve, but maybe there are some significant drawbacks as well.
Yeah, we did not investigate heavily into how many of the Gaussians there should be. For every experiment, we did 10, 25, and 100. And again, and there is definitely an improvement in the reconstruction accuracy the more that you have. Again, the Gaussians have this magnitude value CI that can be used to turn on and off Gaussians. And so you basically would like to have at least as many as there are regions that you'd like to try to learn to describe in your collection of shapes. And 100 seemed like enough to us. I don't think that we would have gotten significantly better reconstruction quality if we had had more, but I'm not sure of that. I'm pretty sure of that. You balance the ability to consistently decomposing the shape into regions, which is easier with fewer of them, versus the details that you get from encoding smaller local regions, which is better with more Gaussians. And so there's probably some knee in the curve there where those two factors trade off.
Thank you. This was great. I also have a question about this Gaussian, because moving from the first idea to the second paper from Kyle, where basically you introduce the implicits into the Gaussians, it brings up this question of like, do you think this is just one step towards some hierarchical structure where you start from a scene, there's like some local structure, then you go even more locally?
Yeah, I think that's a good idea. Yeah. Again, if you like, so how would you represent a city? In computer graphics, they might use a scene graph or some spatial decomposition. Like with an implicit function, how do you represent a scene or a city or the world? You would definitely need some sort of spatial decomposition. It might be valuable to have it be hierarchical, or it might just be that you chop up the world into local regions and then describe them. I frankly don't think anyone knows the answer what's best there, but it does seem interesting to consider hierarchical methods.
Very much so. And actually, I think that's maybe one good question to Gordon, for Gordon to ask the panel about like how to represent the city. That's a very nice question. Thank you so much, Tom, again, for the great talk. This has been great. And with that, I think I'd like to pass the mic to, wait, is Srinath concluding or am I? Sorry. I think I am. Right. Okay. So I want to thank again all the great talks, all the speakers that that really did an amazing job. I also appreciate that most of it, like we had only live talks, which is, I find it much more engaging than pre-recorded talks. And I think all in all, I'm still looking for some feedbacks on Gather, but all in all, I felt like this was a fairly positive experience. Let me know if you think otherwise. While I'm talking, Srinath is sharing the screen with tomorrow's session. We have another session, and we're going to have great talks there with Angela Dai, Niloy Mitra, Noah Snavely, and Jitendra Malik. And then we'll have an expert panel discussion where speakers from today and tomorrow will participate in a panel. Gordon will host that and ask them interesting questions. Maybe one of them will be how to represent the city. So thank you all so much for joining us, and we'll see you in the next session.